the degree was awarded in 2001. Then he worked with the Department of Physics, Institute of Indian Institute of Technology, Bombay, as a postdoctoral research associate on the fabrication of diamond thin films. Thin films. He's by micro sorry thin film and a carbon nanotube by microwave plasma chemical vapor deposition. In 2002, he joined Professor Jean Michael Nunez's group as postdoctoral fellow in the laboratory properties and optic axis of application in C RS and become organic electronics device. In 2005, he returned to India and joined Color Limited in New Delhi and was posted at the Indian Institute of Technology, Kanpur, at the visiting research engineer deputation. Its work developed by the organic diode based on the display for the first time in India. In 2008, he was promoted to the team leader, and by 2012, the group developed by commercial quality of prototypes. In July 2012, he joined the Indian Institute of Technology, Kanpur, as the principal research engineer, and in 2013, he joined the National Institute for the Interdisciplinary Science and Technology as the principal scientist in the photoscience and photonics groups. Under his leadership, a full-fledged device fabrication and characterization facility was set up in the optoelectronics device. At present, he is a senior principal scientist and professors with the academic science and innovation research SIR. His current research interests are efficient lighting using the organic lighting diode, sensing using the OFETs, photo detects, and a large area DSS module. We welcome Professor Dr. K. Narayan Uni, and not only that, he is my old team members and my guidance, and he is, I think, one of the very close friend to me. We welcome to Professor Dr. Narayan Uni for his talk. Regarding the organic light emitting diodes related photo detectors. So I request Professor to share his and start the talk.
Thank you, Dr. Vibhu Prasad Swain, for that rather long introduction. Like you mentioned, it was a pleasant experience for me when we worked together both in IIT Bombay and also in IIT Kanpur with the industry Sample Color Limited. And when he invited me for this, hello, can you hear me?
Yes, I think there is a
somebody
inauguration is going on.
Okay.
So please wait for some time.
Okay.
So because the inauguration is same time.
Oh, that is also same time. Okay, good.
Yes, yes.
We can probably start at 10:30, right?
Okay.
Or,
Okay, so we'll start at 10:30.
No, whatever. I am okay.
Thank you.
How long the inauguration will go on?
It is up to 10:30.
Okay, fine. Then let us avoid overlap. Let's meet at 10:30. No problem.
Okay.
it is this comprehensive training where ATAL Academy, this academy has trained more than few lakhs, more than, in fact, if we only look at 21-22, which would end on 31st of March, we have trained more than 2.5 lakh faculty. And it is an ongoing, continuous process. We are training our faculty members in domain knowledge. We are teaching, we are trying to impart knowledge on pedagogical skills, including highly integrated technological advancements, examination reforms, various evaluation patterns, which we did at AICT's Stanford University. And we are also trying to give a holistic view and invite that various life skills, how time management, how stress management, how gender sensitivity, how inclusivity, all the intangible but some of the measurable aspects can be deeply embedded into it. So we have towering challenges, and with these towering challenges, meticulous, relevant, comprehensive, continuous, project-based, experiential, hands-on teaching, learning process is there. And this is our endeavor, this is our effort to bring in tangible improvement in the quality of technical education. But this can only happen when all of you, my dear, my very distinguished, my very respected coordinators, when you really, really get involved and pay highest priority to the faculty development. Please take them very, very seriously. Quality is imperative, and quality is our utmost dedicated goal. We are trying to bring in peer review assessment and learning curve. That is pre-FDP and post-FDP learning curve and a comparison of that to ensure that we understand whether that the kind of country development program we are delivering at, are they making the right impact? Are they making the right kind of training, or are they actually addressing the training need? We are trying to design them in a manner, we are taking it for the next year, where hopefully, and if everything goes well, part of it would be in an online mode where concepts and other things can be taught, and all experiential learning, all where hands-on training is needed, visit to industry, visit to all the maybe institutes of eminence, participating universities, incubation centers would be in offline. We are progressing towards the blended. I see your cooperation, I see your support, and kindly be with us. Thank you so very much, Vinodji, for being with us. Now I would request our member secretary, Professor Rajiv Kumar, to address this office. Thank you so very much.
Thank you, Mamtaji. First of all, I welcome Shri Vinod Chaudhary ji, Senior Vice President, Houses USA, for being the part of this inaugural function. Our my own colleague, Mamta Agrawal ji, coordinators of 18 faculty development programs, and team ATAL, who is always instrumental in making all these programs success from starting to end, and dear participants. Very happy good morning to each and everyone. Mamtaji gave a very good brief of these faculty development program. I will just share why AICT created all these ATAL academies across country and why AICT is conducting this faculty development program. Although AICT is a regulatory body. Chabri Sahab, I will like to share the genesis of ATAL Academy. In 2018, we prepared the prospective plan of the technical education in the country, and that was prepared that there are all industrial bodies in the country, and they gave us a recommendation. They identified certain areas that which we call thrust areas, and the recommendation was that AICT should impart education or should give approvals in the coming years only in these thrust areas. So we accepted the recommendation of the committee, prospective plan committee, and immediately we start giving approvals only in the thrust areas for the new institutions. But the immediate challenge was who will teach? Who will teach these new areas or emerging areas? Because the faculty, those who are in our engineering colleges, they got their qualification 10 years back, 20 years back, so they are not aware of these new technologies as far as teaching is concerned. So we immediately decided that we should conduct training to our faculty members, and it was not an easy task because imparting training immediately to 6 lakh, 7 lakh faculty members was not easy thing. But we started, and this pandemic gave to us. Actually, we started in offline mode. We could train 40 or 50 faculty members in one faculty development program, and immediately pandemic started. We immediately converted to online mode, and we increased number of the faculty program because the technology always gives you advantage that so, in the in last year we conduct around 1,400 faculty development programs and around 1,60,000 faculty members were trained. Then we were having experience this year. Our ATAL cell, headed by Mamta Agarwalji, they planned 1,500 faculty development programs, and by now, by today itself, more than 2,50,000 faculty members, faculty development programs, successfully attended these faculty development programs, and up to March, this figure will increase, I think, in thousands also. But when you are increasing the volume of something, and when you are conducting more and more faculty development programs, then the quality of these faculty development programs is also a challenge for us. So we realized this thing because we have increased number of faculty development programs. And one more thing, that these faculty development programs, they are being conducted by most of the reputed institutions in the country, say IITs, NITs, reputed universities and the institutions in the country. But still, we feel that we should have a check on the quality of these faculty development programs. So we conducted a team of very, very senior academicians and industries, experts, those who are working in these domain areas, to take the feedback of these faculty development programs. And this review team was not to find the fault in the faculty development programs. It was basically to give suggestions for the improvement of the quality of these faculty development programs. And we got suggestions from our team, and we are analyzing the suggestions. Our ATAL team is working very, very hard how to implement all these suggestions, which are for the betterment of the quality of the faculty development program in the coming years. So this our ATAL team, they are working on it, and the next year when we will announce faculty development programs for the next year, all such suggestions will be incorporated the conduct of all such faculty development programs. So I wish all the coordinators, they will take all these faculty development programs very, very seriously, and whatever suggestions even coordinators wants to give us, I will request our ATAL team that they should also share a Google form for the suggestion to the coordinator, so that we can improve the quality of these faculty development program to the level what is required to the industry. With all these words, once again, I thank all the participants, coordinators, and Mr. Chaudhary for being part of this faculty inaugural session of this faculty development program. And they have got suggestion, Mr. Chaudhary, they are going to help in improving the quality, and your suggestions also will help how to conduct this faculty development program, so that there will be more involvement of the industry in more sessions. There is limited sessions presently for the industry in our faculty development programs, it is mandatory, but we need more and more industry participation should be there in that. So we need your support, we need your help. Also, we will keep on giving us
अब क्यों
suggestions.
टेंशन ले रहे हो इतना?
अरे मुझे ट्रैफिक में टेंशन ज्यादा खाली है
Thank you
ट्रैफिक
so
में
much.
ट्रैफिक में आधा घंटा
Lot of technology and actually that includes mitigate technology that which you have in the future to actually train more than 2.5 lakh faculty members. And as that has already advised them, they have the ability capable seeking all your expert feedback on what are your daily needs towards them. Without taking much time, I would just request Vinod Chaudhary, currently Senior Vice President, to go ahead and complete as I said a while ago. Not only he has been Vice President to study commerce credit protocol, Vice President and Business Head, Commercial Lending and Capital, Senior Manager, Consumer Lending and Bank Manager, Logistics, Marketing, Growth. He's a seasoned professional with more than 35 years of experience working with multinational organizations in different business verticals, be it technology, telecom, financial services, e-commerce, or automobile. He has worked in India for 15 years and roughly 20 years in the United States in very senior responsible positions, delivering consistent results, reporting into executive council and part of the Infosys BPM executive council and head of policy council. Looking to contribute to the government's India initiative, which involves global Indian workforce, increasing digitalization of the consumer and industrial commerce. It could also be an involvement in the role that India plays in other developing nations like Brazil and Mexico industries of technology cooperation.
Hello,
That we are looking forward to
hello,
your
ma'am, sir. The voice is not audible to us.
what best can be done in what we have technological
Voice is not audible.
so very much. Over to you.
Voice is not audible.
Sir, we are not able to listen properly.
It is elaboration session is going on. So after that, 10:30 will start.
For getting to commercial point of view, I was thinking of I have several things to share with you. First of all, I want us to reflect what COVID has done to the world. And it is important because it is very likely that it will be COVID. But our ways of working during COVID will not change. Something very interesting that all of you are dealing with is this virtual learning process. audience knows that a lot of products that we use in our day-to-day life comes out of technology that we develop for some other purpose. Take the example of space research. Often people say, what is the big idea of what they're trying to put somebody on Mars? And to my mind, it is not just getting to Mars. It is also the fact that in process of bringing the technology to get to Mars, invent products that comes into common household. Many of you would know that crack-resistant lenses, high-grade firefighting equipment, things like insulin pumps, artificial limbs. These are all examples that are there today in our life. So somebody could focus on space program. Went out to the space program, buy products. Number of these beneficial things have happened to the society. Thing that I wanted to share with the forum is that similarly there is a particular technology that we bring in. My concern today is what is it doing to our future generation. Today, because of the technology and the ease with which information can be shared and distributed, I can safely say that we have no single source of truth. We're struggling with it. It is technology which is enabling a lot of. To talk to our mother today, the biggest challenge is keeping the kids away from the screen. Almost 90% of the input today that the kids are growing up with are coming through screens. It's worrisome in some ways. But yes, that's nothing but technology. Industry does will continue to be there. I want to look that as a social responsibility, we have to also see how we overcome this challenge that the society experiences. I thought thinking in all this technology. I work in a place where that is where Masaji I was going to respond to your requirement. How do you keep the quality? And we have relationships with our several universities, market leaders or leaders in the academic world. And I'm sure that happy to play a part, leveraging them for the program that India are building. When India is the largest number, I was looking at some numbers. They say we produce 1 million engineering desks. I think we must be close to that number, approximately. The big beneficiary of our engineers are also the Western developed countries.
Hello everyone. Can you hear me?
Yes, sir, you are audible.
So we'll again welcome our speaker, Professor Dr. Narayan Uni. I have it is I don't know why it is.
Yeah, Dr. Vibhu, I think two equipments are on. Probably you are listening from computer and phone. Can you mute one of this?
Where it is going on.
So can I share my screen?
Please mute everyone. Parthiban, Dr. Parthiban, please mute everyone. Everyone should mute. Otherwise, it is yes. Okay. So should we please share your presentation?
Can you see the full screen now?
Yes, yes, please.
Okay.
So I think we have already introduced the Professor Narayan, Dr. Narayan Uni, and I want to say these things. This is sorry for mistake. I have already inaugurate there is no inauguration section. It is not good, but maybe these lectures from Professor Uni will encourage you and learn lots of things from this organic electronics session. Thank you very much. Please continue, Professor Uni.
Thank you. Thank you, Dr. Vibhu Prasad Swain. So as I was mentioning, first of all, let me thank the organizers of the faculty development program on nanotechnology at NIT Manipur. In fact, it is really commendable that these people could organize such a program even during this pandemic time. Now, as somebody mentioned in the inaugural section, now we are starting to learn the advantages of online and offline learning and teaching. So even in the time of pandemic, now I see that many webinars, probably much more than what was happening during the normal time, is happening. And in fact, we can get even Nobel laureates for the presentations and all in many local colleges and universities. So everything has, I mean, a positive side, and that is what I thought. So this is also a good side for the pandemic affected period through which we are all going. So again, as I was mentioning earlier, pleasantly surprised by the call from Dr. Vibhu Prasad Swain, because after a long time, long gap, we could reach out to each other. We knew each other from IIT Bombay when he was a PhD student, and then we were in the same team in the industry, Sample Color Limited also. Okay, so this is how I have organized the talk. There will be, I thought it will be good to have a small introduction to nanotechnology. Even though today and in the coming days, there will be many presentations on different aspects of nanotechnology, and probably you will be saturated, by the end of this course with the terms like quantum confinement, quantum dot, and things like that. This being probably the first of it, I thought I will just touch upon some historical aspects and also some science behind nanotechnology and the various applications of nanotechnology. So we will see some of the applications in photovoltaics and energy storage, also chemical and biosensors and lighting, particularly OLED-based lighting. Since in these kind of discussions and forums, generally people raise concerns about the hazardous nature of nanotechnology. So I thought it will be appropriate to have one word about health hazards of nanotechnology and also the development of nanotechnology in India and at government level, how this is being handled using different agencies. I thought I will give a glimpse to that also. So this is how this talk has been arranged in the next probably 1 hour or so. Let us then start. Okay. So we will have a very brief look at the historic aspects of nanotechnology. It is in fact very interesting to note that from 4th century BC, we knew about these particular properties of the small particles. Even though they didn't call it nanotechnology or anything like that, Swarna Bhasma, which is gold powder, and it cannot be said that it is really nano powder, but people used to make gold powder. Some of these could be nano, some of these could be micro also. And in Siddha practices also, this gold and silver powder has a lot of healing powers. And we knew this, particularly in India and China. This was very popular, these Swarnabhasma related treatments. And in 3rd century BC, Egyptian blue, you all know these silicates out of copper, silver copper silicate or something like that, which is a pigment which could be made into nanoparticles by their particular processes. And this also, like graphene, you could actually split up into nano sheets, 2-dimensional sheets. So it was good to use this in ornaments and to color chromes and things like that. Even excavations have found out many ornaments and other things which are coated with this Egyptian blue, because there was always a possibility to have a conformal coating with this material. That was the advantage. 4th century AD, Lycurgus cups in Rome is another very important step in this technology. This is in fact very interesting because it uses this dichroic property of nanoparticles, that is silver and gold alloy. These cups are used in Rome. When it is lit from light behind the cup, it appears red. And when you look at the cup from the light coming from the front, then it looks green. This is because, I hope all of you know what is meant by dichroic property. Light has two mutually perpendicular polarization, right? So if absorption of any one kind of polarization is much more than the other, that results in the dichroic property. So this, again, all these, could you please mute? Somebody was, hello? Hello?
Everybody must be mute. Dr. Akash Sharma, please mute your this thing. This is the generalized platform. You cannot make a noise in between the talk. Professor, please carry on. Hello? Professor Uni, can you hear me? Hello? Your voice is not coming. Hello? Your voice is not coming. I did not mute anyone. Oh, please.
Yeah, now I am okay. Yes, I hope you can hear me, correct?
Yes, please.
Yeah, okay. So again, in 19th century, colloidal gold becomes very popular in Europe. People knew about the healing properties of colloidal nanoparticles of gold. But everything changed. Normally, in all the discussions in nanotechnology, we come across this statement by Richard Feynman in 1959. In a seminal presentation, he suggested there is plenty of room at the bottom. So what does it mean? When you go down to miniaturized sizes, there are a lot of possibilities to develop new technologies. That was first suggested by Feynman, and in 1974, Norio Taniguchi, who was a professor in Tokyo State University, he coined the term nanotechnology. So in fact, this term is unlike the other linguistic developments. This term was particularly developed from the physics and material science. So nanotechnology, the term was developed by Norio Taniguchi. In 1986, again, in a seminal work by Eric Drexler, an article came out, Engines of Creation, the new era of molecular nanotechnology. That was the title of the book. And in fact, he is considered to be the founding father of nanotechnology. Okay. his PhD thesis from MIT, of course, also gave a lot of outlines how we can work with these new materials and the new technologies. So it's a very, very important person if you consider the development of nanotechnology, still working on several aspects of nanotechnology. In 1991, discovery of carbon nanotubes by our own S. Ijima, who was a research scientist with the NEC Corporation in Japan. And then thereafter, I don't have to give too much details about nanotubes, but all of you know that when these structures are two-dimensional, it becomes graphene, and when you roll, it becomes carbon nanotube, and in a spherical shape, it is C60. Okay, so since I mentioned C60, you see, Robert Gold, Harold Kroto, and Richard Smalley. They all get the Nobel Prize for discovery of Buckminster fullerene in 1996. Fullerene is the soccer ball, football-shaped molecule. And when it is a rugby ball, what do we call it?
यार
When,
वो
when, it
उसका
has
हो
a,
नहीं रहा शुरू संगीता का पेपर है
when it has the shape of a rugby ball, it
संगीता
is
का
called
पेपर शुरू नहीं हो
C70.
रहा है
Okay, so now it is C60 and C70 is also there, particularly useful for
मतलब
making
शुरू नहीं हो रहा है
organic photovoltaic
वो
materials. In 2003, the silver nano from Samsung came. So the silver nanoparticles has a lot of antimicrobial properties. All of you know, even in our fridges, even electronic components, a lot of antimicrobial uh, resistance or antimicrobial protection is given by this coating silver nano, because silver ions will eventually bind with the DNA of microbes or bacteria and will stop the reproduction of this bacteria and ultimately will lead to cell death. So that is why silver nanoparticles are used in even in band-aids. You see this advertisement everywhere that fridges, microwaves, and band-aids all have silver nanotechnology, originally developed by Samsung, which is used in many other applications for wound healing and all. And thereafter, you cannot now give a chronology like this, because multitude of applications in energy, drug delivery, consumer electronics, therapeutics, diagnostics, and whatnot, right from the toothpaste that we start our day with. From there onwards, and in the night, if you apply a moisturizing cream, or during the daytime you have a sunscreen, and your car got a scratch, then you say scratch removal cream. Everything is completely based on nanotechnology. So this is the reach of the area, the field, and the science behind.
Hello, Professor Oni.
Yeah, sorry, I think again I got muted. So yeah, we will.
Please, there is some participants about the clarity of voice, but I heard it is clear from my side, from to me. Your voice is so clear. I don't know that some are means complaining that there is voice is not clear.
Oh, okay. I am also surprised because I got a message saying that it is clear, but I skipped one or two slides. So let me just once again, maybe I can once again unshare and do it.
You can
Okay.
quickly, hello sir, you can quickly share the slides so far once again, quickly.
Yes, yes. Can you hear me now?
Is it okay? It is okay.
Okay,
Please
and you
continue.
can, yeah, you can see the slides also, right? So I just
Yes,
finished this history of nanotechnology and I went to manufacturing.
yes.
Because we are
Yes,
losing
please.
time, let me go fast. So there are
Yes.
two approaches, bottoms up and top down approaches, where in bottom up technology, you start with atoms or molecules, and with the different chemical processes, you go to the atomic and molecular condensation, where different shaped nanoparticles can be created. And in the other approach, top down, you start with the bulk material, and systematically you remove components and bring down to nanoparticle size. So one is starting with atoms and molecules and going to nanoparticle assemblies, and another one is starting with bulk material and coming down to nano-sized particles using techniques like sputtering, chemical etching, thermal laser ablation, mechanical ball milling, explosion process, and things like that. Okay. So what happens when you go down to nano level? A lot of things happen. See, this is an example here I have shown. This 6 nanometer gold nanoparticle is having red color, but when it goes to 2 nanometer, it is having a blue color. Why this is happening? And this is a solution with the nanoparticles. So under UV excitation, you can see the color. It starts with the red when it is 6 nanometer, then yellow, then green, cyan, and then finally blue. That means the band gap of the material is changing. Okay, the band gap of the material changes because its optoelectronic properties change. So now, as I mentioned in the beginning, so you probably will be saturated by the end of the course with this term, quantum confinement. So quantum confinement means confinement in different directions. You bring down the size of the space available for the carriers to move around. So no confinement, then the density of states is parabolic density of states, you see here. So this everybody knows. One-dimensional confinement will lead to quantum wells, thin films like that. And two-dimensional confinement here will lead to nanomodels. Yes. Yes. Hello, can you hear me?
Yes, it is clear. Please
Yeah,
don't disturb in between. There is sufficient time in the end so that everybody will ask questions. So
Yeah, sure.
please, Professor, please continue this talk. At the end, everybody, it is time for the question.
Yeah. Good. So in 3D confinement, in 3 directions, there will be confinement, and accordingly the energy levels will be modified. These are, I think, now in textbook knowledge. No need to go deeper into it. But application-wise, quantum dot displays. So we have worked on OLED displays, Dr. Vibhu and myself, when we were there in Sample, we worked on OLED displays, but now quantum dot displays are there. So what is the principle behind quantum dot display? It is down conversion using quantum dot nanoparticle. So here you have a blue emitting layer. This could be even inorganic LED, very strong blue emission. And instead of having red, green, blue subpixels, we have red, green, blue quantum dot. So this quantum dot will absorb this blue and emit in their characteristic wavelength. So red quantum dots will emit in red, and the green will emit in green, and the blue will emit in the blue region also. Maybe a slightly lighter blue because the band gap changes. So that is how this work. And we have different type of quantum dots, as I already mentioned. This is very, very bright display because you have an inorganic LED which is having a very good brightness, and these quantum dots most of the time they have very good quantum efficiency. So the brightness will be very good in such displays, and the nanocrystal quantum dot displays are very popular in market now. It is coming up as a technology for information display. In fact, one interesting thing is that carbon quantum dot can give red, green, and blue emission together by controlling the size. But otherwise, the cadmium selenide and those kind of materials are used for other, for example, red color. Those kind of quantum dots are available. Now, photovoltaic, I thought about what I will speak about nanotechnology in photovoltaic, but it's a very, very vast field. So instead of going into a particular application, I thought I will take one slide and talk to you about this. So nanoparticle-based conductive coatings are there. In silicon photovoltaics as well as third generation photovoltaic, you need to have a conducting plate, ITO, FTO, and also there will be in silicon technology, there is a silver bus lines and all. These are normally done with silver paste. this paste is actually nothing but a suspension of silver nanoparticles. And ITO is also deposited by nanoparticle-based sol gel technology nowadays. FTO is also done like that. So a lot of applications for the conductive coatings. And again, like just now we saw down conversion nanoparticles. In third generation photovoltaic, some of the active materials may absorb, say around 500, 530 nanometer. So what happens? These nanoparticles will absorb the blue emission, which is not absorbed by the active material, and then emit in the 530 nanometer, so that it is not becoming a waste. So these materials can actually, nanoparticles can actually absorb the unused radiation from the solar flux and then emit in the wavelength region, which will be absorbed by the active material. So that way the efficiency of the solar cell increases. And the third one is plasmonic absorption. I hope all of you know what is meant by plasmon. And when metallic free electrons vibrate in the metal film, they have a characteristic plasmon frequency. So any material which is in the oscillating electric field will absorb more. So that way, this is particularly used in organic photovoltaic. It increases the absorption cross-section of the organic absorber material. And then even in silicon photovoltaic, anti-reflection coatings with nanoparticles are used. For example, zinc oxide nanoparticle, that will create a lot of scattering. So the kind of reflection that may happen normally from the front surface will be avoided. And as a result of scattering, the light can in fact go into the solar cell, and the chances of it getting absorbed will increase. And the very important application is self-cleaning coating. There are two types of coating. One is the hydrophilic coating and the other one is the hydrophobic coating. So hydrophobic coating normally is by controlling the surface energy and also the surface morphology. There will be a grooved morphology. So dust, organic contaminants, nothing can stay there. At the same time, the hydrophilic coating will have a kind of mechanism where a bird deposit or dirt, organic contaminants will be removed by a kind of a photocatalysis in presence of light. So it becomes water and carbon dioxide. So that kind of self-cleaning coatings are being applied by many companies now on their solar panels. Then in light scattering layers, as I mentioned, this will increase the absorption of the solar cells. And in flexible electronics, there's a large potential of nanotechnology. In this printed organic solar panel, whatever these lines that you see, these white lines are silver buff lines, and these are done with silver paste, and also the encapsulation is probably done with the nanoparticle immersed epoxy resins. So altogether, I mean to say that a lot of applications of nanotechnology in the area of photovoltaics. Now, when we come to energy storage, we also had some work on supercapacitor. Supercapacitors are capacitor, but having a higher energy density. And there are also two electrodes and a separator, of course, to prevent it from shorting and all. But energy density is given by half CV square. This is a very standard equation. At the same time, the capacitance is given by epsilon 0, epsilon r, A by B, right? So if you want to increase the capacitance, either you need to decrease the D or increase the epsilon, or you increase the area. So this is where supercapacitors, what we work at least, is to increase the electrode surface area. Because surface area normally is length into breadth. But when it is going to nanostructure, it is actually a different picture. Because the contours will create a lot of surface energy, which is very good for supercapacitor application. We will see what we did with a certain example here. So this is again with MOS2 nanostructure. So hydrothermal reaction. With the hydrothermal reaction, we deposited this MOS2 nanostructures on nickel form, which is commercially available. So this is like a sponge or something. So MOS2 is grown over the nickel form, and you see this is the nanomorphology. All these nickel form wires becomes like a Velcro that you know. So surface area of these kind of structures will be huge, much more than what you really expect. And accordingly, we got something like 10 watt-hour per kilogram kind of energy density. And so such applications are in most of the supercapacitor application. People work with increasing the surface area of the conductive electrode. And of course, there are other possibilities to work with the electrolyte separator and things like that. I'm not saying that there are no other research directions, but in many ways, the surface modification using nanotechnology is an important aspect in energy storage using supercapacitors. Now, when we come to the next two applications which I would like to discuss is organic field effect transistor and organic light emitting diode. So I will give a small primer about organic semiconductors. In 1828, Buller synthesized the urea in lab. Till then, it was assumed that organic materials are available only in living organisms. Okay, and that is why the name organic came in, because people thought the origins will be related to life. 1950s, crystalline organics were being pursued, thinking that it could be a replacement for silicon, which never happened. And in 1970s, organic photoconductors, xerography materials were there for photocopying applications. 1980s, nonlinear optical materials for lasing applications. 1987, first organic light emitting diode was reported. After that, millions of organic compounds have been synthesized. Now, if you look at the physical properties of these materials, they are van der Waals bonded materials. So this is a loose connection between the molecules, not like not like covalent bonding or ionic bonding, which are stronger. And there are sigma and pi bonds. Sigma bonds will give strength for the molecule, and pi bonds responsible for the electro-optical properties. And the important point is there is a weaker delocalization of electronic wave function, or in plain English, that means you don't have any free electron. Okay. Two classes of materials. One is small molecule, and the other is polymer. Okay. Small molecules are small, as the name indicates, small units, and polymers are long chains of these molecules. Electrical conductivity is governed by band or hopping transport. Sometimes polycrystalline materials can be developed, so that is why band transport is also considered to be one mechanism of electrical transport. I think I don't have to go to details of organic semiconductors, but think about this benzene here. And you have this unhybridized pz orbital at every Z. So this is the sp2 hybridization, right? So you have the pz orbital, which is here, unhybridized pz orbital at every Z, and these are the sigma bonds which are shown here. But the unhybridized pz orbital on top will form a molecular orbital, and below the molecular plane also there will be a molecular orbital. So there is a molecular orbital which is where you have the chances of finding the electron, and a molecular orbital where you have chances of finding the electron very less. So this is very similar to the traditional semiconductor picture, right? You have a conduction band and you have a valence band. So that is why they are called semiconductors in the first place. And when you look at the energy configuration coordinate diagram, it is not only the electronic energy levels, but there is vibrational energy levels also, which I have shown here. Okay, so that means for absorption and emission, there are a lot more possibilities, unlike an atomic emission or absorption. So the absorption is broad and emission is also broad. A lot of ramifications of these kind of features in devices, but I'm not going into those details in today's talk. And the conductivity is still given by mu times number density into charge. But there's a difference. Electrons and holes are responsible for conductivity in traditional semiconductors, but polarons are responsible for conductivity in organic semiconductors. Now, what is meant by polaron? A polaron is a charge plus a distorted lattice. So I have shown here a lattice, and the lattice is distorted because of the presence of the charge carrier here. So it is very similar. You think about a net, a football, a volleyball net or something like that, stretched, and you throw a football into it. So wherever the ball hits, there will be a depression, and from there the ball will bounce off. It will reach another place, but the another place you will again create a depression. So you can think that the depression in the net and the ball are traveling together. So the depression plus the ball together is called the polaron here. The lattice distortion and the charge together. So that is what is the polaron. And one major difference is that the conductivity is still given by the Ohm's law. Like this. But in inorganic semiconductors, when the temperature increases, what happens? N increases because you get a lot more free carriers. But in organic semiconductors, the number of carriers is very less. So as I mentioned, when the temperature increases, it is mu that is increases because the vibration of the lattice increases, jumping of the carrier increases, so the conductivity increases in a particular fashion. So this is the difference between organic and inorganic semiconductors, at least in their conductive properties are considered. Okay, so this is a very brief primer about organic semiconductors. Today we are not going into device physics of organic semiconductors. I would like to, if time permits, I would like to discuss a little bit about the interfaces, nanostructured interfaces, not about the actual role of organic semiconductors in devices. But again, in one of my previous slide, I told that when confinement happens, the energy levels will become discrete, and also the band gap increases and things like that. So does it happen in a molecular level? It happens. So for example, you look at this polymer chain, which is shown here. Okay, see the conjugation is shown here, alternate single and double bond. Okay, so this is the absorption of this material. And you connect two such chains with a linker molecule, and still there is no change in the absorption spectra because it is a molecular property. But you attach another chain here, another unit of single and double bond, then what happens? The absorption actually moves to lower energy. Absorption moving to lower energy means the band gap decreases. Okay, so you add more, then it will again decrease, but ultimately there is a minimum threshold point where it will stop. And then suppose if you have a lot more polymeric chains like this, what happens? It will still remain same, but the broadening increases because of the interaction between several molecular chains. So here also you can see that the space available for the carrier to move around decreases. So that is in fact increasing the band gap and the energy levels. Okay. So even though I cannot connect it with any physical principles, I can say that I generally tell this to students that think about some person in a jail. So in movies, you can see that always they move around left, right. They don't sit. So they have more energy because they are confined in a very small room. Put the same person in a large auditorium, he will say just sit in some corner because the energy is very low once you have a larger space to move around. And delocalization, what I just mentioned, it is not theory. It is in fact, it is true. Think about a naphthalene, which is only two benzene rings, and the absorption maxima is something like 220 nanometer. And you add one more benzene ring, it becomes anthracene. So anthracene, the absorption maxima moves to 260 nanometer. That means your band gap is actually getting reduced. And you add one more ring, it becomes tetracene. And for tetracene, the absorption maxima is around 275. So you keep on, I mean, pentacene could again go further. So the space available for the carriers to move around increases. In all these cases, the band gap decreases. As a corollary, you can say that when the space decreases, the band gap increases, which happens in a molecular level and which happens in the bulk level also, where you are actually doing your nanoparticle based technologies. So since I mentioned all these things, seeing is believing. Nanotechnology cannot work without ACM, AFM, TEM, those kind of very, very advanced imaging technologies. Today we are not going into the different technologies, but at least I thought in many of my presentations I show this picture because in 2009 or something it came out, and I never stopped loving this picture because this is an ACM, I mean AFM image of pentacene molecule done by IBM by a specialized AFM, modified AFM, where the cantilever tip was a carbon nanotube. And with that, they could actually take an image of a pentacene, and the electron density is shown here. So this is what I'm saying. Seeing is believing. In fact, whatever we draw on our textbooks is, in fact, really it is like that. Okay. So organic electronics is a part of flexible electronics also today, and organic electronics has come a long way right from the invention of organic light emitting diode. So I discussed this when I was touching upon the development of organic electronics. Three major areas are there. One is the organic light emitting diode. This has become a commercial reality in a display sector. OLED televisions, OLED mobile phones are available, but the domination for the fight is still continuing with liquid crystal displays. Organic based solid state lighting is there, but it is yet to take off. It is not yet there. Okay, it is in the R&D stage. A lot of applications are there, a lot of promises are there for organic based lighting, but it is still there. So quantum dot lighting, I hope one day nanotechnology can create a miracle in lighting also. Organic thin film transistor, most of the applications are in flexible and printable electronics for sensors, wearable electronics, and things like that. But compared to silicon or inorganic materials, the mobilities are still low. So probably 10 is the reproducible maximum mobility that you can get from an organic thin film transistor, 10 centimeter square per volt second. Think about polycrystalline silicon. That is also something, amorphous silicon, that is also something like 10 to 15. And low temperature polysilicon will be probably around 100. And crystalline silicon can go up to 10,000. So that is the kind of range of mobilities where we are competing with inorganic materials like silicon. So there the picture is not very good, but there one can still find applications where a very high level of mobility probably is not required. Okay, so there can be applications where these kind of transistors can also be employed. Then the third one is organic photovoltaic cells. The quantum leap in efficiency yet to happen, because efficiency is reached something like 15, 16 years ago, and now it is 18.4 or something like that. So it is there. One of the problem is the stability also, but with many technologies, quantum technology is also supporting the development of organic photovoltaic cells. But altogether, it looks like hybrids may lead the way. Hybrid means it is not only completely organic, but there may be inorganic nanoparticle like let's say selenide, sulfide, those kind of materials are used. So one can say that it is best of both worlds. So there could be inorganic properties of inorganic materials and properties of organic materials together can in fact make it a much better device. This is the hope of the people who are working on hybrid organic photovoltaic materials. Now coming to field effect transistor, a little bit of a technical introduction is required to understand the kind of nanostructured interface morphology, which I would like to explain in the coming slides. So field effect transistors are MIS kind of structures, metal, insulator, semiconductor. Okay, so this is a metal contact, which is the source and drain electrode. And here we have the insulator, and this is a semiconductor. So what kind of semiconductor is this? Can you understand? Looking at the energy levels, since the Fermi level is close to the conduction band, we can assume that it is an N-type semiconductor. Okay. So before contact, the energy levels are like this. So this is the work function of the metal. This is the Fermi level of the semiconductor, and we have the insulator. The moment you make a contact between all the three layers, then what happens? As we all know, the Fermi levels try to align. This is the energetically most favorable situation. So Fermi levels try to align. As a result, there will be band bending at the interface. And now the thing comes. Suppose if you apply a very high positive potential to the metal electrode. So the metal electrode energy levels are pushed down. You see that? It is pushed down. When it is pushed down, as a result, the bands are bent downwards. And here you see that the conduction band is coming, at some point it is coming below the Fermi level, and that means you will have free electrons here. Free electrons means you have a charge carrier density induced here at the interface. So this is the induced charge carrier density, which will move across the source drain contact in a normal field effect transistor. So you have a insulator, and when you apply a potential to the gate electrode, the energy levels are energy band bending happens. Because of the band bending, there is a charge reduced state here, and these electrons can move when you apply a potential across the source and drain electrode. This is the basic principle of field effect transistor, particularly for the MIS structure, metal insulator semiconductor structure. So we did some experiment here again. So this is a pentasine-based transistor, and we used polymethyl methacrylate, a well-known polymer film, as the dielectric. So this is we looked at the influence of molecular weight. So we used 3 different molecular weights, and we looked at the influence of the dipole moment of the solvent, like toluene, chlorobenzene, NMP. See, NMP is having the highest dipole moment of 3.95, and toluene is having the lowest dipole moment of 0.3695. And if you look at the PMMA surface morphology, there is not much difference, right? But the moment you evaporate bendazine on top of this material, so I have only shown one case here. This is a high molecular weight PMMA film, 350,000 is the molecular weight. And then the film is cast from toluene. So this is the toluene film, this is chlorobenzene, and this is the NMB film. You see the surface features of tungsten film. So with the toluene, you have very small grains. And with chlorobenzene, you have slightly larger grains. And with NMB, you have much larger grains. So for field effect transistor to work very good, have very good mobility, obviously you need to have large grains because grains are akin to single crystals. So within a grain, the charge carrier can move ballistic velocity. But again, at the boundary, there will be scattering. Well-known facts, grain boundary scattering angle. But the problem is that if you need to have a very large mobility, not only large grains will work, but there should be good grain connectivity also. That is one thing. See, here also, these things are not connected. Here you have somewhat reasonably good grain size and a good grain connectivity. And here both are achieved. So obviously these things will get the higher mobility when you actually put in a device. But it depends on the surface energy also. So controlling the surface energy, you can control the nanostructure of the semiconductor. Now, where is the importance? Importance is not only in the mobility. When you actually put it in a device, there are a lot more ramifications in the performance of the device for this kind of structures when you have the structural control. So this we will see with another example. So in this work, we looked at molecular weight, dipole moment, and the chart shows that when you have high molecular weight and reasonably good dipole moment, you get a very high mobility. Similarly, similarly, you have a medium molecular weight or high dipole moment, you get a high. So, a lot more discussions are there in this paper, but I only wanted to say how we can control the nanostructure. So that is why I took this example. Now we go to a actual device. This is a polyhexyl thiophene based ammonia sensor, which we made. So this is the chemical structure of PhD, and this is the ammonia sensor. Here we use an inorganic CO2, so source, drain, and regular 3ST. So this is the fabrication detail. So I will not go into the details of fabrication, but let us see what is happening when we actually do. So the other one, pentacin was thermally evaporated. In this case, the regioregular polyhexyl thiophene was evaporated. I mean, deposited by spin coating. Sorry. It was deposited by spin coating. So all of you know what is meant by spin coating. Spin coating means depositing a film from a solvent. So you develop a solution of the material and flood it on a substrate, and then you rotate the substrate around a perpendicular axis. So the solution gets evenly spread, and once the solvent evaporates, you get a film. So these are the process from starting rest condition, you go to a particular speed with the ramping, and then stay at that speed for spreading the film, and then you come down to rest in a controlled manner. The thickness of the film is given by 2 pi into concentration divided by square root of the angular velocity. So you can see that concentration is more important with regard to thickness than the speed of the rotation. So we did a study in which we deposited regular polyhexyl thiophene, and we controlled this time. So this could be even 3 seconds, 10 seconds, like that. So depending upon the time given for spreading this, the structure and the nanomorphology changes. So we have done with a few timings, but looking at the structural control by spin coating, this is 3 seconds, 10 seconds, and 60 seconds. So the absorption spectrum of P3ST is well known. The peaks around 530 nanometer here. These are for the interchain connectivity. It is showing interchain coupling, and the peaks at the higher wavelength like 560, 570, and these are indicative of the intra-chain coupling. So intra-chain coupling is also very important because you want to have charge carrier moving from one chain to another. At least it should move from the source to drain. So it has to go through several bridges of nanostructures, polymers. So this is what we can control with the spin coating technique here. This is a nano morphology here. So this is a transistor which we made, and this we used for an ammonia sensor. So why it is good for ammonia sensor? Because P3HT is a p-type semiconductor. So the conduction channel is formed by induced holes. But you know that ammonia has this lone pair and all. So when it is exposed to ammonia, ammonia will give an electron density to the channel, which will in fact sacrifice your already available holes and deplete the hole concentration. So your current should decrease. So that is the idea behind this. So we did this with ammonia. See, this is the original characteristic. This is the output characteristic, VDS, IDS characteristic of our transistor. The black characteristic is the original output characteristic at 40 volt VDS and 40 volt VGS. The moment you expose 100 ppm of ammonia, then the current is immediately going down. So this is the sensitivity, or this is how it is used as a sensor. But you flush out all the ammonia by evacuation or passage of dry air or something like that, then it is actually coming back. Okay, so you are getting it here. So this is by controlling the surface morphology, one can increase the active sites and thereby increase the sensitivity of the device. The work which was published, I think, 2018. So when we look at nanostructured offset sensors, the control of surface morphology required to increase the active surface area, because as I mentioned, you need a lot more active sites to get the analytes. It could be ammonia in certain cases, it could be something else, it could be any volatile organic compound also. People have developed many volatile organic compound sensors using organic field effect transistor, but for a higher performance, this kind of a structural control at the nano level is very important. Usually, there is a trade-off between sensitivity and electron property. This is because when you have a very rough surface, you can in fact attract a lot of analyte molecules. But the roughness will compromise your electronic property. The your mobility mess up, your current mess up. So unless you don't have originally a very high current density, where are you going to push it down? So that is a question that you need to have a very good transistor with very good output current. Only then the sensitivity will be good. And then a porous semiconductor, as I mentioned, is preferred. Porosity has been achieved by several techniques. We did this with simply controlling the spin coating technique. But for example, another very good performing device, there is an implantation of polystyrene microspheres with a diameter 10 micrometer on the silicon dioxide dielectric plate. So they implant polystyrene microspheres and then they remove it, subsequent removal of the same. So when they remove it, there will be concave shaped surface morphology, which will in fact attract a lot more ammonia, but it is a complicated process. So we need to have more facile techniques. We demonstrated this with the solution processing, and now we look at what we can do with the thermal evaporation. So in another example, a small molecule based ammonia sensor, which we did, again, this is DNTT, a thiophene based material. This can be thermally evaporated. In fact, it can be solution processed also, but we did thermal evaporation. So this is the device structure. There is a substrate. IQ is the gate contact. PMM, polymethyl methacrylate, the gate dielectric. DNTT is the semiconductor. And we used gold source and drain electrodes for this particular work. Now here what we did is, see, any thin film person, a thin film physicist or a thin film technologist know that thin film growth proceeds via four stages. One is the nucleation, second is the coalescence of islands, and third is the large grain growth, and fourth is the continuous film. So once you have a 5 nanometer film, look at this film. So you have small islands. And when your thickness increases to 12 nanometer, these islands coalesce together. So there will be better connectivity between grains. And when it becomes 15 nanometer, you have very good connectivity, but your porosity suffers. So by intuition, one can say that 12 nanometer film will be much better for a sensor, because it has same time it has simultaneously it has good connectivity between grains, and it has good porosity for accommodating the analyte molecule, in this case, which is ammonia. And we tried these two devices, 15 nanometer and 12 nanometer. In fact, 5 nanometer was not even giving a very good transistor characteristics, because these are isolated. As you can see, these isolated pentasite grains cannot contribute to a very good output current. Okay. So these are the output characteristics of our devices, small molecule based of it. Like I mentioned, the 15 nanometer film has very good drain current up to 20 microamps at 30 volt. But the 12 nanometer film doesn't have that much current. It has only 6 microamps, close to 6 microamps at 30, because the grain size is small, but connectivity is. Then we calculated the mobility and other useful parameters from this device. And when we checked the performance of the device for ammonia sensing, see, it starts with a 0.1 ppm, 0.5, 1, like that, up to 20 ppm. So down to 0.1 ppm of ammonia could be sensed with this device. This happened both with 15 nanometer film and 12 nanometer film, but as you will see, the 12 nanometer film had higher sensitivity for this particular application. So this is before exposure, it had the characteristics here, something like 5 microamps. I showed for the 12 nanometer film. And the ppm of ammonia, this is coming down. And after evacuation, it is going back to the original characteristic. So this is a good reproducibility for the device. And when you calculate,
nanoparticle बनते कैसे हैं?
when you
मैंने एक screenshot लिया.
so when you calculate the, please, can you please mute? So
nanoparticles का एक heading होनी चाहिए.
So when you look at the sensitivity, that means the current without exposure to ammonia minus current with exposure to ammonia divided by current without. So the normal expression for the sensitivity. So the density of the thick film, that is 50 nanometer film, is something like 60%, whereas the sensitivity of the porous monolayer film is something like 80%. So that is the importance of the nanostructured morphology for this kind of sensors, where it increases the number of active sites, the number of locations where ammonia can come and interact with the semiconductor. And these devices had, sorry, this is in fact sensitivity on the y-axis. So this is a the cyclic performance of the device. So this is a work we did and published last year. So from these examples that I showed, offset-based ammonia gas sensor has been fabricated and characterized with both polymer and small molecule. And the dependence of the spinning time on P3ST semiconductor layer, very important. So controlling the spinning time will control the nanomorphology, which will in turn control the sensitivity of the ammonia sensor. The polymer device can sense ammonia concentration in the range 20 ppm to 100 ppm for that particular device. The mechanism of ammonia sensing is attributed to de-doping phenomenon in the P3HC semiconducting channel, which means there is a used to hold current density on the channel, which will be depleted by supply of electrons from the ammonia. But this is a physical thing. So when you flush it out, ammonia will go, then the electrons will go, and you will have the same whole current density, which was previously there. The thickness control improves the porous nature of a thermally evaporated small molecule. Okay. So this is again a technique with thermal evaporation, which myself and Dr. Vibhu all have been working for a long time with thermal evaporation. And so I am still happy with the kind of features that thermal evaporation is giving us to control the structure, nanomorphology, and also you might have come across this glancing angle deposition of thin films, which will again give a different type of nanomorphology, which is good for certain metamaterial application. And in my small molecule study, ammonia down to 200 ppb could be detected, and multi-parametric detection is also possible. This I didn't discuss, but it is not only the current density, but a transistor has several other parameters like surface density of states, the mobility, the on-off ratio, threshold voltage, like that. So we found that every one of these parameters actually changes when you expose it to the particular analyte. So OFET probably is one of the only sensing device which can have a multi-parameter detection, because optical detection works on the basis of increased absorption or quenching. That means decreased absorption, emission, things like that. So there is only one parameter which will respond to the analyte. But in the case of this type of devices, it could be even more. Structural control is very important for optimal performance in any of these devices. So the last of this is the OLED optical outcoupling. Organic light emitting diode, I hope all of you know the basics, because today we do not have time to go to the basics of OLED, but it starts with the glass substrate. Okay, so this is a glass substrate, and there is a transparent conducting coating, which is normally IQ, indium tin oxide coating, and then there is a whole transport layer, and then we have the emitter layer. From the other side, we have the cathode, lower function metals, mostly aluminum, and then there is an electron transport layer. So electrons will be injected from the cathode into the emissive layer, and holes will be injected from the anode into the emissive layer. Okay, so electrons and holes will combine from exciton, which is a quasi particle, okay, within the emissive layer, and when they relatively recombine, you get the light. So this is the basic principle of OLED in a nutshell. Okay. But the interesting thing is that not all the photons that we generate here are coming out of the device. It will be surprising to know that only 20% of the devices are coming out of the 20% of the photons are coming out of the device. This is because of the refractive index mismatch between the adjacent layers. You see here, when the angle of incidence is more than the critical angle, you know that there will be total internal reflection. So which creates a guided wave here. So wave guiding happens and edge emission will be there. And similarly, when light is going from a denser medium to a rarer medium, if it is falling at an angle more than the critical angle, it will be reflected. Total internal reflection may happen here. So light gets lost in many ways. Only something like 20% of the photons will be coming out. This has a very, very important aspect. It's a very important aspect considering the lifetime of OLED device, because you need to have more light. So you will drive the device more and more and the device will die. But if you could get the other 20% here, then you don't have to drive the device at a very high current density. At a lower current density, it will give the same brightness. So that way, it improves the lifetime of the device if you can increase the light extraction, which is called optical outcoupling. Okay. So we looked at it and how to manipulate scattering. So you know, nanoparticle-based scattering. Scattering factor X is given by 2 pi r by lambda. R is the diameter of the particle, size of the particle, and radius of the particle. So lambda is the wavelength. So X is much less than 1, then it is Rayleigh scattering. We are very familiar with this. And when X is close to 1, it is my scattering. And here the forward scattering increases compared to the reverse scattering. And when X is much, much more than 1, it is the geometric shadow that we all know. So we made a polymer nanocomposite film as an extraction layer. We used ZNO. See, ZNO probably you will see in the forthcoming lectures is one of the wonder material which can take any different type of shapes, nano rod, nanosphere, nano flowers, and whatnot. We used nanoparticles of ZNO of around 100 nanometer. We mixed it with a polymer called PDMS, which is a transparent polymer. So we looked at the transmittance. See, so this is the transmittance of PDMS film. When you put nanoparticle into it, you see that the transmission decreases. But when you increase the concentration of the nanoparticle, it is coming back to the original transmission. This is because a property called haze is what is varying. Now haze is given to be diffused transmittance divided by total transmittance into 100. So this is haze. Haze gives how much scattering happens. So PDMS haze is very low, something like 55% only. But PDMS plus ZNO nanoparticle has a very high level of haze. So this can be used in the optical extraction. We made this film and we put the film here. So this is again the OLED structure, which I have shown before. So in the OLED structure, this time I have given the refractive index also. So 1.5 is the refractive index of glass and 1.44 is the refractive index of PDMS. So that is why there is not much total internal reflection. The ray will continue into it. And when it is scattered, the my scattering prevails. So forward scattering increases. So this ray, for example, if the PDMS layer was not there, then this light ray would have reflected back. But instead of that, it is going into the film, and after undergoing scattering, it is going out. But it is not a forward scattering alone. So that is why if you look at the device with the polymer extraction layer, it looks a little hazy because in several directions it is going. And without a PEL, it is a frontal emission only. But again, this kind of devices may not be very good for information display, because the resolution may be lost. But at the same time, you can have this for lighting applications, and that is exactly what we did. And in collaboration with IIT Kanpur faculty, Professor Monica Katia and Professor Shilpi Gupta, we tried to look at the normalized scattering cross-section of these particles. And we found that even though we said we use 100 nanometer particle, the scattering cross-section becomes very good around 400 to 500 nanometer size. This is a simulation. And for the three principal wavelengths, 476 nanometer, 524 nanometer, and 616 RGB, this is what is the good size of the nanoparticle. So we went back and didn't include it here, but went back and checked the SEM of our polymer nanoparticle layer, and we found that some sort of agglomeration is happening in this phase. And due to agglomeration, we are actually getting particles close to 400, 500 nanometer. So that is why we are getting very good extraction efficiency, which can be directly applied into devices. So we did it with red, green, and blue and white device. And this is the example of the white device. You have the red, green, blue peaks. And these continuous lines are the emission spectra without the polymer extraction. And these devices, I mean, the lines with the symbols are the emission spectra with the polymer extraction. You see, there will be very good enhancement in the light which is outcoupled. And for green, if you look at it, it is around a 57% enhancement. For red, it is 38%. For blue, it is 31%. And for white devices, it is 38.56. One advantage of this kind of polymer extraction layer is that it is a flexible film which can be directly applied to flexible devices or rigid substrate. In fact, it may not need any glue or something, because if you can just paste it on the glass without any air bubble in between, then atmospheric pressure itself that will stick onto the device. So we are trying to see what could be the commercial possibility of this kind of materials which we can use. So finally, I think I have come to the end of this presentation. A question normally asked by people: does nanotechnology pose a health hazard? As I mentioned in the beginning, right from our toothpaste up to our moisturizer, which we use in night, day-to-day applications are multifaceted. But it is true that nanoparticles might cause damage to lungs. Ultrafine particles from, for example, diesel machines, power plants, incinerator, they can cause damage to human lungs. Even when we burn materials, the aerogel, some of this can be nano-sized carbon can go into your lungs. Something which is going into your lungs, it's very difficult to take it out also. So this is both because of their size, as they can get deep into the lungs, get buried into lungs, and also because they may carry other chemicals. They can interact with chemicals, for example, VOCs in the atmosphere, and take with that load into the lungs and create trouble. Nanoparticles can get absorbed in the body, skin, lungs, and digestive system through food, for example. So this may help create free radicals. The most common free radicals are like singlet oxygen and hydrogen peroxide. These can cause cell damage and damage to our DNA. And once the nanoparticles are in the bloodstream, they will be able to cross the so-called blood-brain barrier, go into the brain and create havoc there also. So there are several issues. The human body has no natural immunity to new substances. So any new substance, that is why even when we try a new drug, sometimes the body thinks that it is the foreign body which is toxic and try to reject it. So this happens in our body. But a lot of applications, lot of features and advantages. So once when we think about it, you should ask this question whether advantages are more or disadvantages are more for nanotechnology. I hope there will be other discussions today covering these particular aspects. And when you look at nanotechnology in India, a mission on nanoscience and nanotechnology, Nanomission, Department of Science and Technology in Government of India, they have a program. You can go to this website. They fund projects based on nanotechnology. And the METI, that is Ministry of Electronics and Information Technology, also has a nanotechnology initiative. So these two nodal agencies are supporting a lot of nanotechnology related research in the industry. And so summing up, nanotechnology enabled products have become part of our daily life. Both top-down and bottoms-up approaches are pursued in different cases. So nanostructure influences the interface properties, which I tried to explain with some examples. See, I am no nanotechnology scientist per se, but I use the nanostructured morphology for applications like sensors, field effect transistor, LEDs, and things like that. And as we discussed, health hazards are there, but the advantages most of the time outweigh the disadvantages. So careful application. It is true with any technology, not only nanotechnology. Take nuclear technology, for example. So any technology, this has this catch. It has to be there has to be a careful usage of these materials. Only then one can really use it for the complete benefit of mankind. So since this is a FDP program, I understand there are a lot of teaching faculty. I thought of discussing this also. These are the opportunities for faculty. There is a Indian National Science Academy visiting fellow. One can join for the 1 to 6 months. One can apply for this fellowship. So they will give a fellowship per month, and you can work in a national lab like our lab, CSIR lab or IAC, up to a period of 1 to 6 months. They can apply. This will give you a good exposure about what is happening at the frontier. Select a good lab, apply, go there, and see what is the kind of research. Then there is a SERB TARE program. TARE means what? Teacher Associateship in Research Excellence. That is the expansion of TARE. This is a very good program, I would say, for 3 years. And you can find out the details from this website. I think this call is also open. And it will give 5 lakhs rupees for research expenditure per year. And only condition is that the faculty should stay at the host institute at least 90 days per year. And the thing is that your host should be able to give a certificate that you have attended the lab for 90 days. Then you have 60,000 rupees per year, that is 5,000 rupees per month or something like that, a small fellowship. I'm not talking about the monetary benefit here, but the kind of academic benefits that you may accrue from attending this programs are enormous. You can apply for this program for 3 years, a contingency grant, and also a small fellowship. And for institutions under UGC, there is a Raman postdoctoral fellowship for 1 year work in USA. You can select good labs like Professor Ajay's group, for example, working very good in nanotechnology. So I encourage that you guys should apply for this kind of fellowship and try to go and find out what is happening at the frontiers of research, and then come back and start a program. Institute. Okay. So I would like to acknowledge the Department of Science and Technology in the Australia-India Strategic Research Fund program, and also the Materials for Energy Storage program. And SERB, I have a core research grant. Of course, my parent organization, CSIR, collaborators like Professor Monica Petia, Professor Shilpi Gupta, Professor Dr. Agi Ragaman, and my students, Dr. Anjali Soman, Rajiv, Manu, Vipu, Anjali, all contributed to the kind of results that I shared today. And now, since I mentioned about the Lycos Cup in Rome, I thought I will conclude with a photograph of this. So see, when the light is coming behind, it appears red. And when it is the light is coming from the front, then it is almost green. This is because of the dichroic property, which Romans, ancient Romans probably didn't know, but somehow they realized that these nanoparticles of silver and gold immersed in the glass matrix could create this type of wonders. Thank you. Thank you.
Thank you, Professor Tony, for a informative talk. So I request now it is open for this faculties from various institute and research scholar to ask questions if you have. So please, it is open for all audience to ask questions if you have any doubts.
Should I ask a question?
Yeah, please.
Myself, Dr. Pankaj Kumar Singh from IIT BHU.
Go ahead.
Your presentation was very nice, sir, regarding the nanoparticles. You have mentioned the negative aspects of the nanoparticles, as so many cosmetics and foods are coming with the nanoparticles. how we can be safe from those poisonous effect of the nanoparticles?
In fact, I think for nanotechnology as such, is there any regulation in India? I don't know. But for each product, it is there. So for example, the silver film that we find in bakery products like cakes and sweets, burfi. Sometimes there is something which they say that you can eat. So these are approved by the Food and Food Safety Authority (FSAI) of India, and like that, I think for each product there is a regulation for toothpaste, for sunscreen, and for food items like that. Other than that, I am not aware of any umbrella restriction on use of nanotechnology. So I think it varies from case to case. That is my understanding.
Thank you, sir.
Any other questions?
So, am I audible?
Yeah. Please.
Good morning, sir. Thanks for the fine presentation. We request you to, if possible, to share these presentations of this session as well as subsequently, so that it can be referred later on also and to crystallize the concepts further.
Definitely, I will forward this presentation to Dr. Bibhu Prasad Swain, and he will share with all of you.
Yes, thank you very much, sir. Thank you. And this request is for all sessions because certain things get clarified during the course of the actual presentation. Some question answer also further helps. But still,
Yeah, I have in the first slide. In my first slide, I have given my email ID. So later also, if you want to
thank you, sir.
some particularly from this, you can contact me. I will be happy to help. Okay.
Yeah, thank you, sir. Please share. Thank you.
Anyone from any other questions?
Good morning, sir. Sir, one question is, what's a polaron means? My understanding was it's a polymer with a charge. So you have told me that depression, what is the charge in the polymer? Can you explain?
Polymer has, polaron has nothing to do with the polymer. It is in fact polarization. So lattice gets polarized because of the charge. So that lattice polarization plus charge is what is polaron. So there is, in polymers it may happen, that is another thing. But it can happen in other semiconductors also. So that polaron's POL is coming from polarization of the lattice because of the interaction with the charge.
Hello, sir. Can I have a question?
Yes.
I am Dr. Meenakshi, sir. What is the safety of nanoparticle as a drug carrier?
Nanoparticles are used for drug delivery. I know that. But my understanding is that most of the time benign nanoparticles are used. For example, TiO2, those kind of things are anyway there in our tablets, the coating of the tablets and all. Some kind of nanoparticles are there which are benign. And I think they functionalize these drug molecules on benign nanoparticles, which can go into the body and go out without creating a trouble. That is my understanding, but I am not an expert in drug delivery, so I don't know for sure. Okay.
Okay, sir. Thank you, sir.
Actually, I request Dr. Meenakshi to wait second or third days. There is the 2 or 3 talk on drug delivery and other biomedical applications of nanotechnology. I request to join and understanding these things.
Okay, sir. Thank you.
Any other questions?
I think it is okay. I once again thank the organizers and particularly Dr. Vibhu for inviting me for the presentation today. Thank you. Thank you all.
Thank you, sir, very much. Thank you very much for keeping my applications and give a informative talk. And I think all faculty members here are beneficial for this thing. Thank you very much once again. Thank you. So Next talk is Dr. Mukul Gupta. So he will easily join before 5 minutes. He told me. So wait for. I think we should wait for another 10 minutes to attend that lecture. I want to clarify, is it the talks are audible clearly?
Yes, sir. It was audible.
Yes, sir. Audible.
Yes, sir. Yes, sir.
Okay. Thank you very much.
सकते हैं because I cannot वैसे तो शरद जमीरा के पेरेंट्स ने भी
Good afternoon. Sorry,
Yes, hello.
good morning. Can you
Yeah,
hear
Dr.
me?
Vibhu. Yes, I can hear you. Can you hear me?
Yes.
Okay, great.
Uh, can we start these things? Please share your PPT if it's possible.
Yes. Hello. I hope you can see my screen, right?
Yeah, thank you very much. Actually, Dr. Mukul Gupta, he has pursued his BSc in a DAV college, Muzaffarnagar, a MSc from IIT Roorkee, PhD from UGC DAE Consortium for the scientific research Indore, and he has postdoc from Paul Serrer Institute, PSI. He has joined with the UGC CSR consortium for 16 years, and now he is a scientist G. And he has more than 200 ACI publications, and lots now it's going on. So he has emerging up means expert in this thin film science and technology. And today lecture is on transition metal nitride thin films synthesis and emerging applications. So I over to Dr. Mukul Gupta regarding his talk, and thank you for accepting this invitation. Thank you very much, Dr. Gupta. Please.
Thank you, Dr. Bihu Prasad. It was really, I mean, it's really nice to hear on this occasion of faculty development program, and I would have liked to come personally over there for the meeting, but because of this pandemic condition, it is not possible. So we'll try to give you some flavor of the type of work that we are doing, and what are the type of work that, I mean, you can benefit from using the facilities that are available at UGCDA CSR. So you know that this institute UGCDA CSR is a based laboratory which provides state of art experimental facilities to all um, scientists and professors in the country. So with this short of introduction, I mean, I will try to give you some flavor of the work especially related to metal nitride thin films, and why these metal nitride thin films are important and what are their emerging applications. So I'll try to cover all these details in about an hour and a half. So just tell me like 5 to 10 minutes before when I have to finish. Otherwise, I'll continue. Yeah. Okay. So again, thank you very much for the invitation. So, and I would like that I mean, this presentation should be interactive. So, whenever you feel like, you can interrupt me and ask a question, and then you will also benefit, and then I will also not be monotonous, because speaking in front of this monitor doesn't really give any sense unless there is some interaction which is involved. So please interrupt me and ask question whenever you feel like. Okay. Yeah. So this is the outline of my presentation. Yeah. So here what you can see is that this is the outline of the presentation. So I'll give a brief introduction about UGC DA CSR. So UGC and DA, these are two prominent institutes in the country, and they together have come to form a consortium for scientific research. What is this and how you can benefit from utilization of this UGC DA CSR? Then I will give a very brief overview of the facilities that I'm looking after, okay, so that you can directly interact with me. And the mechanism through which you can access these facilities is through collaborative research scheme of UGCDA CSR. Then today's topic, which is about metal nitrides. So I'll give again a brief introduction. Then synthesis of these thin films is a inherent part which involves a lot of work, and I'll try to give some flavor about the deposition or preparation of thin films. Then I will talk about some recent works that we have carried out on some compounds, for example, cobalt nitrides, then titanium nitride. So I think the time will not permit to talk about more, so I will restrict myself to these two systems only today. Okay. Yeah, so you know that UGC has established some inter-university centers. Some of these centers are very well known. For example, NAC, everyone knows because you directly interact with them for the accreditation. But there are 3 research IUCs of UGC. Okay, so one is IUAC in New Delhi, where hello, yeah, any question, any doubt or something? Okay, so these 3 research IUCs, one is Inter-University Accelerator Center, which is at New Delhi. Then IUCA, you know that they deal with astronomy and astrophysics at Pune. And yeah, and then our institute, which is UGCDA Consortium for Scientific Research, which is at Indore. Okay, so this UGCDA CSR actually started somewhere around 1990. So already like 30 years back, we started with a broad objective of developing competence and promoting research in frontline areas of science and technology in Indian universities by providing institutional framework for optimum utilization of major research facilities established by the Department of Atomic Energy. So for example, Dhruva reactor at BRC Mumbai, VECC at Kolkata, and then synchrotron radiation sources at Indore. So, you know, these prominent facilities of DAE, okay, so that they can be accessed by university. So that is why this our institute has come up, and we have been placed in the proximity of a big DAE laboratory. So you know there are 4 such big DAE facilities at Indore. We have synchrotron radiation source. At Mumbai, at the Dhruva reactor, we have neutron scattering and complementary facilities. At Kolkata, we have experimental and theoretical nuclear physics together with VECC. Now, this Kalpakam, we have a node, but very soon there will be a center where there are medium size but high tech facilities of IGCAR, Indira Gandhi Center for Atomic Research, Kalpakam. So, at these 4 major locations we are placed, and you can use facilities of any of these centers, but Indore is the headquarter, and there are these 3 centers. Okay, so this is a glimpse of various areas in condensed matter, physics and chemistry. So we have large scale facilities that involves synchrotron and neutron and ion beam. Then electron spectroscopy and diffraction, spectroscopy of various types, then low temperature and high magnetic field facilities, then material characterization using a range of facilities like AFM, SEM, etc. Then synthesis of samples, be it say thin film or single crystal or bulk, and sample preparation and conditioning. So as I said already, we have these 4 centers. Indore is the headquarter, and Kolkata, Mumbai, and Kalpakam is the newest center, which is going to come up very soon. Okay, so those who collaborate with us, they know that, I mean, so throughout the country, you can see that we have a presence everywhere. More than 350 universities and institutes are collaborating with us, and our facilities are becoming popular. I mean, you can see that the number has been increasing. There was a dip here because of the pandemic condition. Otherwise, we have a very nice outreach all over the country. Okay, so with this a brief introduction, I'll come to an overview of the facilities that we have in our laboratory. Okay, so in our laboratory, we are working on thin films and multi-layers of various types like metal nitrides, oxynitrides, oxides, carbides, etc. So we synthesize these thin films using sputting techniques, then process them using thermal processes like thermal annealing. Then one of the key areas that we are working on is self and interdiffusion in various stacks of films using SIMS depth profiling. Then we also use X-rays and neutron reflectivity extensively. Then characterization using like XRD, and the novelty is that we have this soft X-ray absorption spectroscopy, which is the only technique in India. I mean, because you know the synchrotron is at Indore only, so there are instruments which are available, and these are like unique in the country because nowhere else you have the synchrotron. So I will cover about some thin film deposition using the sputtering technique. So we have three sputtering units. One is this ion beam sputtering. Then this is a homemade system. This is a magnetron sputtering, 2-inch magnetron sputtering system. This is also a homemade system. And here this is a state-of-art commercial system bought from AJA in USA. And there are various options in these systems which are also available. Briefly, you have you can do samples and sample transfer using a load lock. Then there is a substrate heating and cooling, and you cannot see here, but then we have now placed reed. So you know you can monitor the growth using reflection high energy electron diffraction, and suppose you grow an epitaxial film, so you can get the diffraction from the film during the growth itself. Okay. Then we also have a residual gas analyzer and so on. Then after deposition, so processing using this ultra high vacuum rapid thermal annealing. This is a thermal annealing system. This is secondary ion mass spectroscopy, and of course you know this XRD. Then I'll spend some time on this because this is a novel technique. Like I mean, novel as well as unique technique, which is soft X-ray absorption spectroscopy. So this beamline we have developed by ourselves with the initial funding from DST, and this provides a very nice opportunity to probe various types of materials that I will describe a bit later. Okay. Yeah. So there are more details about this, and you can just I will not go through all of these, and it is not also possible to go through each one of them. So I will just restrict myself to magnetron sputtering as well as this uh, soft X-ray absorption spectroscopy. Okay. So as I was talking about this reed, which is a sort of a novelty in our growth chamber, because you will not find it very often. So here what is there that these are magnetron sputtering sources, and we have put a electron source, okay, electron beam. So this is the electron source, 35 kV electron source, which provides a beam of electron. Now this beam of electron will fall onto the sample which is growing inside this chamber, and then it will get reflected at a grazing angle, and it will carry the information about the sample which is grown inside in situ. Okay.
નથી મારે સમજાવવાનું જ છે કેમ કે apparatus available જ નથી કયા
Yeah, so this is an example. So this read option, in situ read option, we only put in our system like a couple of years back, and this is one example where we have grown iron nitride thin film on a gallium nitride substrate. So only thing is that, I mean, to get such images, we need single crystalline substrate. Okay, so you see there are certain spots coming because of the I mean the periodicity of the single crystal, and then when you start the growth, you still see these streaks, which tells that the sample is grown epitaxially. But if you go very thick, so you see these spots, which means that the sample has now become sort of polycrystalline. So from doing the diffraction measurement, you can just see that this sample is indeed has grown epitaxially, and this is a phi scan which confirms that the growth is taking place along a certain direction. Okay, so I mean, this is just to give you a flavor that you can do, and you just see that I mean, you do not measure only one sample. I mean, you are you do not measure, say, so when this growth is taking place, so you record this growth through a video. Okay, so you get a lot of data points of diffraction at various points, and then you can just see how the lattice parameter is changing, like the d-spacing is changing as a function of thickness. You see that there are certain transition taking place in this sample. So there is a like changeover at 2 nanometer and then around 2.5 nanometer. So since we are doing this growth and monitoring the growth in situ, we can see very small changes that are taking place in this sample. So what happens here is that there is a strain driven structural transition that takes place with an increasing thickness when the critical thickness is about 2 nanometer. Okay, so this facility can also be used through our within our program that I will explain just now. So this is a glimpse of various type of materials that we have deposited in our laboratory. So like oxide, nitride, single elements, thin films of individual elements or multi-layers, etc. Then this is a thermal annealing system. So this is a UHV type UHV rapid thermal annealing. You can heat a sample at a ramp rate of 100K per second. Okay, and this is a homemade system where you can do normal thermal annealing. Okay, so I was talking about this beamline, which is at the synchrotron radiation source at Indore. So RRCAT is an institute which is like 10 kilometers from here, and here we have a we are a couple of synchrotron radiation sources. One is Indus 1 and the other is Indus 2. So I'm talking about because Indus 2 is much larger synchrotron. So there are various beam lines. Okay, so there are like 26 beam lines. Most of them are already working, and you can go to the RRCAT website and you will find details about each of these beamline. But broadly, if I have to categorize these beamlines, so there are like three categories. So one is scattering of X-rays, spectroscopy techniques, and then there are these other beamlines which involves imaging, lithography, diagnostic beamline. So for diffraction, you can do X-ray diffraction, X reflectivity, small angle scattering. So these are the beamline: BL12, BL11, 12, 13, 18, 21. Then spectroscopies of various types. You can do X-ray absorption, photoemission, fluorescence. These are the beamline. And these are the beamlines like BL4 for imaging, BL7 for lithography, and then there are a couple of diagnostic beamlines. Okay. So it will not be possible for me to cover all of them. So you can just visit the website of RRCAT to get information about the various beamlines. But I will cover to some extent BL1 beamline, which is developed by UGC CSR with the help of DST. Okay, so this beamline, so this is the Indus 2 bending magnet source, and then this is the layout of the beamline. So it is ultra high vacuum beamline, 35-meter long, and here you can see various uh, various so in a beamline there are various components. Okay, so one is like this polarization selection aperture, which defines the polarization of the light. Then this is a key component which is like pre-mirror, which selects, because you see when the radiation is coming out from a synchrotron, it has lots of wavelengths. Okay, right from optical to I mean soft X-ray, then hard X-ray. But you need to select some window of this radiation, and this pre-mirror, for example, in this case, will cut all the radiation which is above 1.5 keV. Then this radiation will fall onto grating monochromator, spherical grating monochromator. Then there are 3 of them. Then you can select a certain range of wavelength. Then there is a post mirror which is here. Then the beam is focused at the sample which is somewhere here. Okay. So what we do here, we measure the absorption of X-rays as a function of energy. So it will give information about the absorption H, and this absorption H carries a lot of information about the hybridization of the atom that is taking place with the nearby element. Okay, so okay, so let me go here. Yeah, so this is again some statistics and the outreach of the beamline. These are like the number of publications and about number of samples, etc., number of users. So the beamline started like in 2014, 2014, 2013, so almost like 7 years, and it is now becoming very more and more popular, and a lot of people are using the beamline in various fields. So not only physics, I mean chemistry, then there are people from geology and various other areas. I mean, because what is required is that any sample which has these elements like so let me just yeah, so in this beamline, like there are 4 different type of experiment we can do. So XAS, where we can measure thin films, bulk, solid, any solid sample can be measured. Then we can also do magnetic circular dichroism, which provides information about the magnetic state of the sample. Then this is like in situ growth plus XAS. It's a test we have done. Then in situ depth profiling. So using ion source, we can take out we can sputter off the sample and measure the what is inside. So the beamline provides the information about various elements. For example, key edges of these low Z elements. So boron, carbon, nitrogen, oxygen, fluorine, and up to sodium you can get the K edges. Okay. Then L edges of 3D transition metals, M edges of 4D transition metal, and to some extent N edges of 5D transition metal. And then there are some rare earth like europium, GD, TB, cerium. You can get access. So within say 100 to 1.2 keV, this is the energy range, and you can utilize any absorption edge within this energy. Okay. So just to give you a flavor, I mean these are the some measurements that we have carried out, and we will actually talk about this sample cobalt nitride. This is a cobalt mononitride, and there was a debate about the type of structure. So when you do nitrogen KH measurement, you see that there are certain features and they match very well with zinc blende type structure. Then you can do complementary information. So this is like this. So this is BL1, and you go to BL9 where you can measure the cobalt KH. This also gives a sort of information that the experimental data is very close to the zinc blende type structure. Okay, so using these two like nitrogen KH and cobalt KH, it was possible for us to establish the type of structure. Similarly, I mean, so since I am working on nitrogen KH, so these are like some results of nitrogen KH. So this one is in case of chromium nitride. Okay, so here what you see is that this is nitrogen KH in chromium nitride, and there are some changes when you do, so for example, add oxygen. Then this is a graphene sample, graphene oxide sample. Okay, so nitrogen doped graphene oxide sample, and here also you see a prominent peak, which is sort of confirming that the nitrogen is actually bonded like N2 in this case. And this one is magnesium nitride sample. Here, what has been done is that in these samples, there are sort of various type of so this is magnesium doped gallium nitride, in fact, and so you see that there are various features, and you can then model to know what type of vacancy or what type of defect is there in this compound. So nitrogen KH we have already probed in various nitride elements, nitride compounds like aluminum nitride, vanadium, scandium, chromium, titanium, niobium, gallium, iron, cobalt, nickel, Mn, Pt, and then there are various other. So this is just one possibility. So you can also do oxygen KH. So oxide materials also you can probe very easily. Then carbon-based compounds one can also probe. So this beamline gives an opportunity to probe these, I mean, the KH of low Z elements, so which carries a valuable information about the local structure of the sample. Okay. Okay. If anyone has any question. If not, okay. So you can visit our website and then you will find this user portal. So there are two ways through which you can utilize the collaborative research scheme of our consortium. A long-term project which gives access for 3 years with the possibility of a research student. Then you can always apply for a particular experiment through one-time CRS, and you just submit, apply for a particular experiment, then you get the experiment done. Even if you have a long-term project, you have to always apply through this one-time proposal. Okay. So this is the website, so csr.res.in, and here you can see this user portal, and you just follow the steps, and then you can utilize the facilities. Okay, so with this I have covered the brief introduction about our institute, overview of facilities, and then the collaborative research. Okay, some message was there. So now I start to talk about today's topic, which is transition metal nitrides. Try to give you a brief introduction. Okay. So transition metal nitrides, you know that I mean nitrogen, if you see, it is abundant element, right? 78% of the atmosphere is nitrogen. But the low chemical activity, reactivity of nitrogen, and very strong and stable NN bond. NN is a triple bond. So with the bond energy is roughly 10 eV, which is almost like twice of oxygen. So you will not see many nitride compounds in the nature as you see what in case of oxides. So what you require is to, I mean, you have to break this molecule, and then N becomes available, and N can react with the metal or a element to form a nitride. Okay, so synthesis of nitrides is rather difficult, but once you have these nitrides, many of these nitrides are very stable. So for example, these early transition metal nitrides like titanium nitride, etc., they have a very high melting point, I mean, much higher than their pure metals, because they make covalent bonds. Okay, so very strong covalent bonds. And nowadays in a range of research areas like refractory ceramics, photocatalysts, thermoelectric, superconductors, photovoltaics, solid state lighting, permanent magnets, piezoelectrics. In all these areas, some nitrides are becoming as an alternative and cheaper material as compared to other ones. Okay. So that is how these nitrides are becoming popular in research. Okay, so like these two-dimension transition metal nitrides, they have high conductivity, so they can be used at electrocatalysis, and their electrochemical stability allows them to use in super capacitor, lithium sulfur batteries, electrocatalysis, lithium ion batteries, and so on. So there is a recent review, you can just go through this, or there is another review where people talk about various type of nitrides like semiconductor nitride, then superconductors like niobium nitride, and so on. Then magnetic materials like magnesium, iron, cobalt, waste. Then piezoelectric like scandium, combination of so these are ternary nitrides like scandium aluminum nitride, scandium gallium. So instead of binary, you can also have these ternary ones, which are really very useful for a variety of applications. Okay. So broadly, one can categorize these nitrides as I mean, when we talk about transition metal nitrides, so like early transition metal nitrides or late. So it is simply like titanium, vanadium, chromium, for example. They come early in a transition, like 3D series. So we call them early transition metals, and their nitrides are early transition metal nitrides. The On the other hand, iron, cobalt, nickel, they come late. They appear late in the series, so we call their nitrides as late transition metal nitrides. Now, the basic difference between these early transition metal nitrides and late ones is in terms of their enthalpy of formation. You see, early transition metal nitrides have very low heat of formation, okay, in the range of say minus 200 to minus 100, in this range, okay. But the late ones have very less negative or sometimes even positive enthalpy of formation. Okay, so if you go along the series, you will find that this heat of formation is negative, so it will increase actually. Okay, so which means that it is much easier to form an early transition metal nitride, for example, scandium, titanium, vanadium, as compared to a late one like iron, cobalt, or nickel. So this is the fundamental difference between like various nitrides. So the same will apply even to 4D or 5D. Okay. Now these different metal nitrides have different applications. The early ones, TIN, for example, has a very hard, it's a very hard coating actually. It is corrosion resistance, then diffusion barrier, etc. Scandium nitride also has a high hardness, very high mechanical strength. Chromium nitride is also oxidation resistant coating. Similarly, vanadium. NBN is also superconducting. So these early nitrides have a large range of application, and a lot of people have probed them, and there is a vast amount of literature which is available. But if you see the late transition metals, nitrides, so you will find they are not so much. Uh, Primarily because you see that their heat of formation is very high. So it becomes very, very difficult to form a late transition metal nitride, for example, cobalt nitride. But in recent years, so people have formed these nitrides either using sputtering or some other chemical method. And what has been very interesting in this development that for energy applications, cobalt nitride, for example, has come up like a very cheap alternative. So in this work, people have tried to replace cobalt nitride with platinum. So you know platinum is very expensive, and it is a very good electrode material. Uh, so what they have done is they have compared platinum with cobalt nitride, and it has a very similar type of efficiency as cobalt nitride. Okay, so cobalt nitride can be a very cheap alternative for platinum. So this is what people have tried to show in this work. Similarly, people are talking about nickel nitrides, then various other even iron nitrides, etc., or combination of these like iron nickel, for example. So there is a vast amount of opportunity which is available to probe these late transition metal nitrides. So this is the example which I have already talked about. So what you need to do, you need to make a nanostructure material in such a way that it has this type of structure. Then it is like very much comparable to platinum. Now you can tune the thickness. You can even make this film like almost like transparent when the thickness is low, and flexible type devices can also be made using of cobalt nitride, for example. Okay, so now we will talk about a little bit about synthesis and study of transition metal nitride films. So as we have already seen that this energy in the heat of formation will increase around 3D, 4D or 5D series as one goes from say early to late. Okay, so what makes it rather difficult to make metal nitride when the formation energy is high. So when the formation energy is negative, so we have various type of range of like M2N, M3N, M4N. Then, but what you can do is that if you break this nitrogen molecule to N, then you can shift this. Okay, this is sort of what is known as convex hull in binary metal nitrogen space, and under constrained equilibrium condition where you make N which is available, so you can rather easily make these various type of metal nitrides. Okay, so cracking of nitrogen molecule is possible in the reactive sputtering process, and by benefiting this, one can make various type of metal nitrides. So you can see this in this space, right? So like iron. So very few nitrides are available. There is, because of less formation energy, we have Fe8n, Fe4n, then Fe3n, then Fen. Whereas in case of say Ti, you can see this is very sharp, okay, because TIN has a very low formation energy. So immediately Ti will become TIN, and in fact it becomes very difficult to form other nitrides like Ti2n, Ti3n4, etc. You will not see them. Okay. Similarly, in case of niobium, it is like you can get NBN, sometimes even NB2N. But the late transition metal, when the formation energy is low, you have a range of compounds that can be formed. Okay. So we'll talk about some synthesis that is like using sputtering, and before I go into too much of go into too much of these properties of these nitrides, let me just explain a little bit about sputtering technique. So sputtering technique we can do using various methods like using a DC or RF or pulse magnetron. So what happens is that when you take energetic ion beam, okay, so there is an energetic ion beam, and if it is incident on some material, so what it will do? It will knock out some species like sputtered particles which are positive or negative ions or neutrals. Okay, So sputtering as such is a very old phenomena, but only in like last 50 years or so, it has been effectively used for deposition of various type of nitride, various type of coatings, not only nitride, but also a range of compounds, oxides, carbides, pure metals, etc. So this is how sputtering can be seen. Like there is a ion beam which strikes the same target, then there is sort of mini explosion takes place, and then the chunk of the material will go out. And this material consists of various type of the material which is coming out. It consists of ions, electrons, neutrals, and so on. What defines the sputtering is the quantity which is known as sputtering yield. Okay, so this sputtering yield is a function of the primary ion beam. You will see it follows this type of curve, which means that sputtering will increase, sputter yield will increase when you increase the energy. But if you go to too high energy, then it will decrease. So, can anyone guess why the sputter yield is decreasing when you increase the energy? Because I need some feedback from you people. Are you listening to me? Can anyone guess here? Yes, please try. Please speak loudly. I'm not able to hear. Pooja Kulkarni. Yes. I don't know if you people are listening or not. Hello.
Then please continue.
Okay. See, why the sputter yield is increasing? The reason is very simple. Okay. See, when you increase the energy too much, then this ion which was coming will go deep inside. Okay. The penetration depth will be much larger. That is how the material, it will become hard for the material to come out. Okay. So that is why this sputter yield will decrease. So there is no point in increasing the energy too much. You can keep the energy low and do sputtering. That is how the sputtering is a very economical way of doing thin film deposition, because you do not need ions of very high energy. So when you have to produce ions of high energy, it becomes very, very costly. Okay. But we are fortunate because sputter yield is significant even when the energy is low. So this is the expression of sputter yield. It depends on various factors. The primary factor, which is like M1 is the mass of the ion, primary ion, which is incident on the target, and M2 is the mass of the target. Okay. So this is how the sputter yield is defined, and here alpha is a geometrical factor, like the angle of the incident. E is the energy, ion beam energy, and so this expression is only valid when, say, E is less than 5 kV or so, 10 kV.
Excuse me, sir.
Yes.
Whether activation energy is also working in this point?
Not the activation energy, but so there is a like so you see binding energy of the target U. So you need to have binding. Go across the binding energy. Binding energy is only few electron volts. Okay. So the moment your energy of your ion is more than few electron volt, you are already crossing uh, the binding energy. Now, if you have even like 300, 400 volt or electron volt, it is more than sufficient. Okay. Activation energy is something different, because so binding energy is going to play a role. I hope it's clear to you, right?
Yes, sir.
So like you can just follow this reference if you want to read more. Now, there is another thing which is very important actually. Now here what I have plot is a number of atoms which are sputtering out as a function and their energy. So now these are sputtered material. Okay, so this was the ion energy which is incident. Now this is what is coming out. So you see that the energy, so the peaks around say 5 to 10 electron volt, and there is a distribution. Okay, so already this the energy of the atoms which are coming out, we call them adatums. So this is the adatums, so their number as a function of energy. Okay, so what you see that already you have the energy which is like 5 to 10 electron volt, and it's quite a lot, because if you just compare using say thermal evaporation, for example. So in thermal evaporation, suppose I am heating one target which has a melting point of 1000 degree. So the maximum energy corresponding to the 1000 degree you can very easily calculate is equal to kT. Okay, so kBT, kB is like Boltzmann's constant, and then you will see that in case of thermal evaporation, the maximum energy that you are getting is a fraction of electron volt, like 0.5 or 0.3, 0.03 electron volt or so. Here you have already very high energy. So the advantage of this high energy is that when these atoms reach the substrate, they still have some way of moving around, and so that they can attain a minimum energy configuration, leading to very high quality thin films. Okay, so this
Sir,
is
what is
various.
the geometrical factor, sir?
Yeah, so geometrical factor is like the angle of incidence, right? So suppose you have ion which is coming at 90 degree. Okay, so it will, so sputter yield will change with respect to the angle of incidence. Okay, so suppose your angle of incidence is grazing. In that way, the penetration will be less. Okay, the penetration will increase as you keep on increasing the angle. So your sputter yield will also increase.
Okay.
So normally in a sputtering system, this angle of incidence etc. is fixed. You don't need to worry about. Only thing is that you can change the incident mass and the mass of the target atom. Okay. So these are various type of sputtering which we can do, like ion beam, DC, or RF sputtering, or magnetron sputtering using DC and RF and high power impulse magnetron. I will not go too much into details. These are again a view of various magnetrons. This is like a 3-inch magnetron. This is 2-inch diameter. So okay, yeah. So
એ કેસે આપણે નહીં પૂછું મેન્ટરોને નહીં જોવાનું યાર, એ તો શું આપણે જો એક સુમિતભાઈ કે ગોપાલભાઈ થોડી કાઢ દે, એમનું કામ નહીં એટેન્ડન્સ નું. હા, એ થોડી કાઢ દે, પૂછી લઈશું એવું છે તો એવું કેસે જોઈએ.
Pooja Kulkarni, you are
Yes,
supposed to be removed from this lecture. Why you are making noise?
okay. So I have somehow got this. Yeah. So now I'll talk about some recent results on our samples. So if you have any question, whatever I've covered up to now, you can ask me. Then otherwise I will go to this the topic, some recent results on cobalt nitride and titanium nitride. Okay. Yeah. So as we have talked about this late transition metal nitrides, and already we talked about formation energy. So cobalt nitride is actually rather curious. So these are like some theoretical work which was done by this Japanese group in 2014. Okay. So if you see like iron nitrides, so their formation energy is negative, and you see this Fe8n, Fe4n, Fe3n, even Fe2n and Fen. Okay. So then comes nickel. Nickel, I mean, it goes a little bit up and then it comes down. Okay. So what we are talking about is okay. What we are talking about is a particular case which is Fe4n. Okay. I don't know. There's some. Yeah. Yeah. So Fe4n or tetra transition metal nitride like M4n. So these are very interesting compound in recent year from a magnetic point of view. So they have anti-perovskite type structure, and they are very good candidate for spintronic applications. Okay. So what you can see is that I have listed these three. So Fe4n, CO4n, and Ni4n. So among them, CO4n has a positive enthalpy of formation, which means if I want to form this CO4n, it is going to be a very difficult task. Okay. So nevertheless, there were some attempts, and as I go along, I will try to show that the previous attempts were actually not successful, and by understanding this chemistry about the formation of cobalt nitrides, we could make this single phase epitaxial cobalt nitride thin films. So these are predicted phases of cobalt nitrides. We have CO8, CO16N2, CO4N, CO3N, CO2N, CON, and even under high pressure and high temperature condition, you can get this polymeric type compound, which is CON2. Most of the people have evidence up to now this CO3N and CON. Okay. And CO4N we have synthesized. Okay. So if I compare, say, for example, with iron nitride. So iron nitride is a very simple case. You take iron and start to put nitrogen. You can see that you get this Fe3n and then Fen. And if you raise the temperature, you can even get Fe4n, Fe2n, etc. Whereas in case of cobalt, uh, what you see is that immediately you can see that okay, when I increase the nitrogen amount to like 75% or so, I can get some mononitride phase, but otherwise I get very strange shape XRD pattern, which means that it is very difficult to get a single phase cobalt nitride phase otherwise. Okay, so I mean, as compared to iron, you can immediately see that it is not very easy to get a single phase cobalt nitride phase. You get very strange mixed phases. So there were some attempts which were made to make this cobalt nitride thin films. So this was a work which was carried out like 20 years back by this Japanese group, Ashara et al. And they also end up very similar type XRD patterns where there is a mixed phases like CO3n, CO4n, which are coming together. So immediately people thought, okay, I mean, because the enthalpy of formation is positive, so it may not be a good idea to make these samples at room temperature. One needs to increase the temperature so that one can make a single phase cobalt nitride phase. So deposition at high temperature was a very easy remedy which was suggested. So 10 years later, this group of, again, this is a Japanese group, Ito et al. So what they have done is they have claimed that they have made epitaxial CO4 and thin films, and using molecular beam epitaxy, they have deposited these samples and they have studied its magnetic properties. Now, what is the problem? The problem is that when they deposit these samples at a very high temperature, say 450 or 350 degrees centigrade, what they have found that the lattice parameter of their CO4n, what they claim as CO4n, was coming out to be much smaller. So the theoretical value of CO4n lattice parameter is 3.73 angstrom, 3.74 angstrom. But what they were getting is 3.52, which is much smaller. Now, if you see the lattice parameter of FCC cobalt, it is very close, like 3.54. So there could be a chance that rather than synthesizing CO4n, they have synthesized FCC cobalt and mistaken it for CO4n. So this is what we will try to see. So like they also studied Fe4n. Okay, so in the same group of Ito, they deposited first iron nitride Fe4n thin films, and here what you see that the theoretical lattice parameter of Fe4n is 3.795. What they have got is 3.79. Very nice. Okay, almost 100% matching. But in case of cobalt, it was not the case. Right? As I told already. So Fe4n, this group has made at high substrate temperature. So what they thought, okay, when they have successful in depositing very good quality Fe4n films, why not to take the same recipe for the growth of CO4n? But when they do so, they got much smaller value of the lattice parameter. So the theoretical value is 3.74, and what they have got is 3.52. So they try to say that there was a negative expansion and so on, try to somehow justify it, but if you see the literature very carefully, so what you will find that when people are depositing this CO4n sample at a high substrate temperature, their lattice parameter is smaller. So when some people have grown at a lower temperature like 435, so they have slightly higher value, but still it is very far from the theoretical value of 3.74. Okay, so maximum they achieve is like 3.6. So there is a trend that if you raise the temperature, this lattice parameter is decreasing, and it is actually going towards the lattice parameter of FCC cobalt. Okay, so I have tried to understand this, like what is going on, and why these tetra metal nitrides are important. So as I said already that their spin polarization ratio is very high, almost like 90 to 100%, especially CO4 is much high. And what is also very interesting is that their magnetization, the saturation magnetization, is also much larger than their pure metals. So for example, pure iron is 2.2 and the saturation magnetization of Fe4n is 2.4, much larger than pure metal. Similarly, in case of cobalt, it is slightly higher. So in spite of the fact that you are putting like 20% nitrogen in the metal, you still have a large magnetic moment. So very high spin polarization ratio and the large magnetization makes this CO4n a very favorable compound for spintronic applications. But unfortunately, you see that people, when they tried, they could not get the lattice parameter matching to the theoretical values. Okay, so this is how. So in case of Fe4n, we have no problem at all. But in case of CO4n, there is a problem that the experimental and the theoretical value of the lattice parameter is not matching. So with this aim, we thought that, okay, why not? So there were some other attempts were also made in between. So this one is from a Spanish group and so on. So we sort of started to work on this problem like 5-6 years back. So we thought, okay, let us keep the temperature at high and try to study the cobalt nitride phases. So we simply deposited samples by varying the nitrogen partial pressure, and so we have deposited samples at various partial pressure. So keeping the substrate temperature to 523 K, then what you see is that like 25, 50 or 75 or 100% nitrogen, you have very similar type of structure which is coming up. Okay, normally what would you expect that there will be like various type of nitrides giving rise to various structures, but you end up sort of a similar thing. Okay, so then we also studied this magnetic property using polarized neutron reflectivity, and to the surprise, like when you are sputtering cobalt with pure nitrogen, 100% nitrogen. Even then, because see, cobalt mononitride is non-magnetic. Okay. And the moment you put some cobalt nitrogen into cobalt, the magnetic moment should decrease, but it was not happening. Okay. So the very straightforward answer to what is happening is that it appears that nitrogen diffuses out from cobalt nitride when the growth is taking place at high substrate temperature. So N seems to diffuse out. Now to prove the point that nitrogen is indeed diffusing out, so what we did, we measured the nitrogen self-diffusion. So what we did, we prepared a cobalt nitride sample at room temperature, placed a 15 nitrogen marker layer, then of 2 nanometer between 200 nanometer of CON. Now we have a SIMS depth profiling instrument which gives which can differentiate between the isotopes. Okay, so this is a natural nitrogen and this is 15 nitrogen. Now if you measure the depth profile, what you will find that there is a peak which is corresponding to nitrogen 15. Okay, it's very easy, like because you have this 100 nanometer of CuN and then 2 nanometer of CO 15N and then again nitrogen. So this peak is coming because of this 15 nitrogen. Now simply as you heat this sample, when you reach like 525 or 523 K, 250 degrees centigrade, this peak disappears. So why this peak is disappearing? Because already at this temperature, this nitrogen gets intermixed completely. Okay, so which means that when we are depositing this sample at 523 K, all the nitrogen is diffusing out. What we are left with? We are left with pure cobalt, FCC cobalt. Since FCC cobalt has a very similar structure. So CO4N is also FCC and FCC cobalt is FCC. Only difference is that there is a nitrogen which is inside which expands the lattice. Okay, so FCC cobalt is like 3.5 angstrom lattice parameter and FCC CO4N is 3.7. Okay, so when the growth was taking place at 250 degrees centigrade, the nitrogen is diffusing out. Now you just remember the work of ITO. So they were depositing at much higher temperature, like 450. So it appears that all the nitrogen has diffused out, leaving behind FCC cobalt, and that was mistaken for CO4. So now we have this like catch-22 kind of situation, because if you deposit the sample at low temperature, you end up with some mixed phases. But if you increase the temperature, then nitrogen is diffusing out. So what can be done to deposit this sample? So this is how the diffusion measurement here, and then we also measure diffusion in various nitrides like FeN, CuN, NiN, there is some correlation, so I'll skip this part. And this is what I was talking about. So we have then deposited samples at various temperatures, and you see that lattice parameter is increasing as you put various amount of nitrogen here, even at room temperature. Okay, so so it is possible to get this epitaxial phase, provided you get some support from the substrate. Okay, so here in this case, the substrate was lattice matched with CO4n, and that is how we can get this CO4n with the lattice parameter, which is like
What's
very close to the theoretical value,
yeah, yeah.
5.7 angstrom. Okay.
Validation वाले को
Okay. Is there any question or any doubts? Somebody is speaking. Deepika Arora, do you have any question? Okay, so then we have taken various type of single crystalline substrate, and as these epitaxial films grow on say MgO or lanthanum doped aluminum oxide substrate, there is some strain that can then that has we have probed, and this was the work which was published like a couple of years back. So using a support from the substrate, it was possible to grow this CO4n at room temperature itself. So these are various publications which are like coming from this work on cobalt nitride, and I have just tried to cover maybe a couple of them. So it is not possible to cover all of them. So you can just go through them, and if you have any question, you can come to me at any time. Okay. Now, how much time do I have?
Yes, you have another 15 minutes.
Okay, perfect. Thank you. So, to give you because not many people work with these magnetic materials. So the another example which I have chosen is titanium nitride. This is sort of much well-studied system, and even there we could find that there was certain issues, and we have tried to address them. So here in this case, we have attempted the growth of titanium nitride thin films using high power impulse magnetron sputtering, and also using ion beam sputtering. Okay, ion beam and high power impulse magnetron sputtering. And these are the three publications that have come out last year. So one is in thin solid film, the other is material chemistry and physics, and then other one is applied surface science. So I'll talk about these three publications in 10 to 15 minutes. And again, please ask me any question if you have. So titanium nitride, maybe you know, it's a wonderful material actually. So it has so very first property of titanium nitride that it has a gold-like appearance. So very similar to gold. You can see that it has a gold luster. Okay. And it is also biocompatible, so people use in tooth implant and so on. Then it is a hard material, so it is used for protective coating in high temperature environments such as supersonic jets or these tools which are used for milling, etc. It is also used like a decorative coating. So you just coat titanium nitride, it has a very wonderful luster like gold, and this will not go because it is a very hard material. Okay, even so that it has a very high melting point, which is like more than 2500 degrees centigrade. And very recently, as an energy material, it is becoming very popular in electrocatalyst, in counter electrode and dye synthesized solar cell. As I said already, it is biocompatible, and it is a complementary to metal oxide semiconductor. So because of low loss, it is also a low loss plasmonic material in visual frequency. So there is a very nice review article on the growth of these conductive nitrides, and if you are interested in you can just follow this. Okay, so this is from uh, group in Greece, I think, in Spasalas and Material Science and Engineering. So this is a very nice review which has come out like a few years back, 2018. Please follow it. It is on conductive nitrides. Okay. So titanium nitride, it has a very well known NaCl type structure, and when the stoichiometry is 1:1, the predicted density of TiN is 5.4 gram per centimeter cube, which is even larger than pure titanium. Okay, so pure titanium is 4.5. Huh? But people have made these TiN films over various years, and X in TiN X has been found to vary from 0.6 to 1.2. Okay, very large variation. Now, even the density of TiN films has been found to vary in a large interval. So some people got a value which is as low as say 4.1 gram per centimeter cube. On the other hand, some people got very high value of 5.7 gram per centimeter cube. Now, depending on X in this TiN, one can vary the density of the film. There were some attempts to understand the correlation between the density and the stoichiometry. So as you reach to say sort of 1:1 stoichiometry, then the density will peak. Okay, so this is a nitrogen to titanium ratio. But where this peak could be, so there, I mean, there is a large variation here. Okay, so where this stoichiometry could be and where this peak could be, this is still debatable subject, because you see that the theoretical density was somewhere here, but then people have got much larger value. So why the density is even exceeding the theoretical density? Because that maybe you can put more nitrogen, or you can go nitrogen richer side, which will increase the density. This is still not known, but we have tried to see like how much density one can get by tuning the growth conditions. Okay. So there was some work from this group in Greece, Pasalas, and what they have done is that they have tried to vary the bias voltage. So you know that in sputtering, when you grow the sample, you can provide some negative bias, okay, DC bias, so that you can attract the ions to deposit on the substrate. Now, what they have found that as you increase the biasing voltage, the density increases. See, this is the density, and then this is some sort of void fraction that they have calculated by combining the spectroscopic elapsometer and X reflectivity. So, as you keep on increasing the negative bias, this density of the volume fraction of voids comes down and the density increases. As a result, what they have found that the density has 1:1 correlation with the hardness and also the elastic modulus. So larger is the density, larger is the hardness or the electrical uh, elastic modulus. Okay, sorry, elastic modulus. It actually goes like this, almost linearly. So, as I said already, people thought that the theoretical value is 5.4, but even a higher value is coming. So either the theory is wrong or the experiment is wrong, we don't know. But these higher values have been reported by several people. Okay. But the highest value which has been reported so far by this group, this is like 5.7. You can see here. Okay. 5.7 gram per centimeter. So nowadays, people are growing these TIN films using high power impulse magneton sputtering, and then a group from IC Bangalore actually was collaborating with us. So where we have grown these samples using high PIMS, and what we have found that when we increase the power, the density increases. Okay, so with DCMS we were getting a density of say 4.2, but when we increase the power to 16 point, to 2.6 kilowatt, then we get slightly higher value, and at 16.6 kilowatt we get almost like 5.47 gram per centimeter cube, which is almost like close to the theoretical value. At the same time, what we found that when we increase the uh, power during further deposition, the film becomes smoother. Okay, so this decay is becoming less. But still, the value which we have got is only like 5.47, not close to the value even when to what these people have found, Pastelas et al. In 2000, in the year 2000. Then this higher density has some advantages. I don't want to go into detail. Sorry. So we thought of growing these samples. So what we have seen that when we grow films smoothly, we have high density. So this is the work that we published last year. This is synthesis and study of highly dense and smooth TIN thin films. Okay, so we tried various things. One of them was to vary the energy of the incident rays. So you remember I talked about variation of the energy, primary ion beam energy. So we are using an ion source. So here we can just change the energy of the ion source. So when we use 1 keV and without any interface, we get a density of 5.42. But if we decrease the energy to 0.5, we get a very high value, 5.7, much higher than the value which was previously reported. But when we use a TI interface, which means when we grow TIN film on a TI interface, we got much higher value, like 5.8, which is maximum up to now by anyone. So by decreasing the ion energy at the same time using the TI interface, we could get the highest value of the density. So this is how it looks like that this is the reflectivity pattern. You see that even if the nominal thickness is 100 nanometer, we can see very nice oscillation in the reflectivity pattern, which gives the understanding that the films are smooth, as well as there are various here what you see is that um, in this sample, for example, there was a preferred orientation around 111 and 220 direction, and this peak goes down, but this orientation becomes 111, and film becomes 111 oriented when we use lesser energy. But then we also put a interface, and this also increased the density. Like you can see that by using TI interface and low energy, very high value of 5.8 gram per centimeter could be achieved. So the role of energy, according to serum calculation, that the titanium atom energy reduces by 20% when we reduce from 1 to 5.5 keV, 1 to 5 half keV, 500 dB. So what happens that if you reduce the titanium atom energy, so in that way, this atom will not actually produce any defect. So in that sense, the surface roughness will decrease. The consequence of the variation of atom mobility is enhanced 200 reflection by occupying the lowest surface energy site, which favors the closely packed plane by lowering the overall energy of the crystal. But the TI interface actually provides a template for the growth of these smoother and denser TIN thin films with low surface roughness. So why this is happening? Because there is a coherent atomic matching between TI 2220 TI plane together with the 111 plane of TIN, which helps in the minimization of interfacial strain. And the combination of the two was seen in terms of smoothest and the densest, and the film with the maximum density so far, TIN thin films with highest density which we have achieved. Okay, you can follow this publication if you are more interested. At the same time, we have also studied the interface of TI and TIN to measure the interdiffusion. I think I will skip this part and not go too much, but then what I can just say that if you use this TIN as a barrier, and if the thickness is say around 5 nanometer or less, there is certain significant amount of interdiffusion. But if you take 10 nanometer of TIN, it is actually, it will not interdiffuse up to a very high temperature, okay, up to say 773 K. Otherwise, here itself you can see that this peak has gone already at 773 K, which means there is an interdiffusion. So this is again some depth profiling details. I will skip this, and now again using the beamline, we could get the information about different nitrogen sites. This also I will skip. So with this I come to the end of the presentation, and I like to acknowledge all my students who have been involved. So for example, in CON work, Nidhi and Seema, Salesh in NBN, which I did not present, Nidhi and Seema in situ read, and Sushmita in case of TIN. And I acknowledge all my collaborators who are listed here. I'll also thank DST for providing the opportunity for carrying out experiments, and also some support from NFFA in Europe is also acknowledged. So with this, I would like to thank you, and please ask if you have any questions.
Thank you very much for lots of information, informative talk. I now it is open for these questions. So if do you have any questions, then please ask our speaker.
By the way, this is Sachi Sputa, which is nearby Indore. So whenever you come to Indore, you have a chance to visit. Yeah, please ask if you have any question.
I have very means I am curious about this some of the facts if these nitride based thin films.
Yes.
One is the how is they about stress, because you have deposit around 400 degrees centigrade temperature of thin films, but when it will comes to room temperature, there is stress and strain developed. Then what is the role of stress in these thin films?
Yeah, so this is a very important question that the important topic that you have raised. So there is, there needs to be a trade-off. So for example, there are various things like, for example, the case of cobalt nitride which I have presented. Okay, so there we cannot raise the temperature, because if we raise the temperature, then nitrogen will go out of the system. In case of titanium nitride, you can still grow the sample at higher temperature, but many times people use this TIN as a heterostructure, which means there is a TIN and then another coating, then other coating. Now, if you do this type of stacking at high temperature, so there is certain amount of interdiffusion. So you want the deposition to take place at lower temperature. Now, at lower temperature, because this stress will also develop. So what can be done is that if you do the deposition at a lower temperature, at the same time, if you make the compatible buffer layer, for example, in case of TIN, if you use TI as a buffer layer, so it will release some of the strain because of the coherent matching. So you have to find some sort of a interface layer which can reduce this stress. So, I mean, this is like in case of suppose when we are growing this iron nitride things. So there we use TIN as a buffer layer. Okay. So for growth of TIN, we are using TI. So then what we did, we take TI, then TIN, then FEN. Okay. So this is how you can find out a suitable lattice matching of the substrate. Otherwise, you can use a single crystalline substrate, which has a lattice matching with your compound, and you can get epitaxial thin film.
Hello, sir.
Yes.
Can anything be said about the contact or tribological related performance of these nanomaterials films?
Yeah. So I talked
Interparticle
about
contact.
this titanium nitride, which is a very good tribological material because it has very fantastic properties. I mean, so just 1 minute. Yeah, I mean, you see here. So it is a extremely hard ceramic material, and it is used as a coating on titanium alloy, steel, carbide, aluminum components. So only thing is that what we have found or very puzzling is that why the density of the TIN varies so much. So people have found that the density is varying in a large interval in between say 4.1 to 5.7. Now we know that control of the stoichiometry, then there are three important things. One is control of the stoichiometry, other is that low roughness. So if the roughness is large, then also you lose some of the properties. Okay. So these and the density itself. So one has to optimize all these things to get a very good quality of these materials like TIN. Yeah.
So I have one
Thank you, sir.
question, doubts.
Yes.
Is there, because you are doing in a low temperature,
Yes.
is it in room temperature there is some addition problem between the thin film and the substrate you face?
I mean, TIN films we have grown on a single, I mean, this silicon or glass substrate, and also on a TI buffer layer. So you are correct that there is an addition problem, but then in sputtering, if the thickness is say in the range of within say 100 200 nanometers or even 500 nanometers, this addition problem is not there. But if you go to very thick coating of few micron, then the stress will play a role in the sense that stress will become so much that the film will come out. Okay. So for that purpose, either you have to use a lattice matching or like some buffer layer to reduce this stress to build up. So the key is that you do not allow the stress or minimize the stress. I mean, some people actually use this TI buffer layer in this case to reduce the stress, or use some moderate temperature where the interdiffusion will not be so much, but you can release the stress.
What are the suitable pressure you have taken for the this kind of deposition? Because you didn't mention this pressure for your process.
Yeah. So this is also another very important point because see the pressure. So the base pressure should be as low as possible. You know, when the base pressure is say high, so you have lot of water contained in the chamber. So now this water, it can react, and water and oxygen, these two are the most important culprits. Okay, so water can react with titanium and it can form some hydroxide, or oxygen can react and it can form some oxynitride. This will also give some additional properties, increasing stress and so on. So the base pressure you must keep as low as possible. So in our chamber, we always go in the range of -7 or even 5, -8 in that range, because ours is a high vacuum system. This is not a ultra vacuum, but we do substrate heating to remove the water content from the substrate. And then if you grow, because when you do sputtering, invariably you have to use some gas. So the gas purity also matters. So use as pure a gas as possible, so that the partial pressure of the oxygen and the water will be low. So by taking care of these things, one can improve the quality of the film.
Thank you very much. Any questions from audience?
So as I said already, I mean, all our facilities are available free of cost, and you can come here and you utilize our facilities. We will even provide the travel, etc., and our accommodation, food, etc. also when student is coming from a university. So please feel free to ask any question, and if you are interested, you are welcome to come to our place.
So I think there is no more questions now. If you have any questions, then you can direct contact by this email.
Yeah, so email I have already listed here.
CSR at the REC. So thank you very much once again, Dr. Gupta, and very nice talk and lots of information. Thank you very much once again.
Yeah, thank you, Dr. Vibhu. It was very nice to be part of your program, and it's always a pleasure. So I also am looking forward for you to visit and
Thank you.
utilize.
Thank you.
Yeah,
Thank you.
yeah.
Thank you. Thank you very
Okay.
much.
Okay.
So now we stop this lecture now. At 2 o'clock, there is another lecture. So for this time, so another, I think 30 minutes is there for rest. So we'll go for the next lecture. Thank you very much. And
Okay, so I'll leave the meeting now.
thank you.
Excuse me, sir.
Yes, yes, yes.
Sir, what will be about the attendance, sir? Feedback form and other things.
Attendance, we are taking one this technical staff is there, so he will
Okay.
take your attendance. So don't bother about these things. And finally, this at the end of this FDP, there is a 2 hours means multiple choice questions, and the questions are collected from this all the speakers. So there is 100 number of questions, and they all are evaluated from that day only. Okay, final day.
Sir, any feedback from sir?
Feedback, we will take this thing. I will send feedback to all of participants. Okay.
Okay, on the last day, sir.
On last day.
Thank you, sir.
Okay. Thank you very much.
कॉलेज वाली जी जैसे कुछ
Professor Vibhutibhushan Nayak.
Yes, Professor Vibhu Prasad Swain.
Please share your PPT.
We'll start now.
It's 154.
So we'll wait for another 5 minutes, then we'll start.
Okay.
2 o'clock, maybe.
So Vivo, it is visible. So, chart. Share, sharing. Okay. Now it is visible. Okay. How are you, Vivo?
I am okay.
It's a nice for faculty development program, and I listened first lecture. It was a nice presentation by Dr. Unni. Good job.
Actually, he is my old colleague in IIT
Okay.
Bombay also and IIT Kanpur. So,
Okay. I just started, then after that I went outside, means home, then that's why second lecture I did not attend. Just partly, 5 or 10 minutes I attend. So we'll start or we'll wait for...
yeah, please show your PPT, then I will introduce you.
Okay. So I will stop the video and it will be better. Video.
Share your PPT, yeah.
Okay.
Please share your PPT.
It's fine. It's visible.
But PPT, yeah, it's now it's okay. Okay, full screen. Okay, okay. Good afternoon, everyone. I think we should start the last session of this today lecture. So the speaker is Professor Vibhuti Bhushan Nayak. He pursued his BTech degree from National Institute of Technology, Raulkela. Then his MTech degree from IIT Kharagpur, and his PhD degree from IIT Bombay in a Department of Metallurgy and Material Science. Then he joined NIT Raulkela from in 2006, and is now the professor in ceramic engineering department. And he has lots of experience in magnetic materials, and now he's specialized with the luminescent materials, which is based on the nanostructure as well as various properties of ceramics. He is also the couple of postdoctoral experience in Taiwan. Then he has
only visited.
He has only visited. Okay. Then he has finished 4 projects, and I think 5 PhD students, and now his expertise lectures on phase and photoluminescence characteristics of oxide-based nanostructure materials for luminescence application. I welcome Professor Vibhuti Bhushan Nayak for his talk and for this session. Thank you very much, and for inviting receive my acceptance for this talk. So now it is over to Professor Vibhuti for his talk. Thank you very much.
Good afternoon, everyone. Is it visible, the lecture slides?
Yeah, it is visible.
Yes, sir. It's visible.
Thank you, thank you, thank you. Thank you, Dr. Vibhu Prasad Swami, for introducing me. And I have some experience in magnetic material during my PhD. But when I joined NIT Rourkela in 2006, it is very difficult for me to start with magnetic materials because facilities was not there, and I find out some of the possible materials and some characterization tools to finalize my research area. So from 2006 onwards, I started some materials point of view and the synthesis of nanomaterials, and to correlate the phase and photoluminescence characteristics. And we have explored different types of oxides and some borate based nanomaterials for different luminescent applications. So my today topic is, or my lecture is related to phase and photoluminescence properties or characteristics. Basically, if you see the phase of different materials and it's related correlated with photoluminescence characteristics related to different emission intensity, your different asymmetric ratio, color purity, and CI coordinates. So these are the 4 part of photoluminescence characteristics, how it is related to oxide based materials. Hello, some voice is in background. Okay, thank you. So we are discussing about the phase and photoluminescence characteristic of some oxide based materials that we will discussed in this lecture series. So first of all, I'll tell you the research what we are doing in NIT Rourkela, that is related to material processing. So material processing or synthesis, you can take any type of wet chemical route you can choose, but we prefer to prepare a nanomaterials that will also focus here. So material processing and different types of materials like composite materials, we have cermet, that is anode materials, nickel zirconia based materials for solid oxide fuel cell, magnetic dielectric composites, polymer derived ceramics, and some rare earth and non-rare earth based strontium aluminate based phosphor materials. So using this borohydride route, there are other techniques like sol gel, precipitation, auto combustion, hydrothermal, and solid state route are available. I mean, you can choose, but the agent, that sodium borohydride, that will give you a porous nano and go for different applications. Like we are focusing here some rare earth based and so we are focusing on which is what we laboratory, that is solid phase white light generation emitting phosphor materials, polymer derived photoluminescent films, luminescent ink, and some logo or text on the polymer film and fingerprints. So for security and anti-fraud domains. So these are the PhD scholars, already 4 passed or degree awarded and the 3 submitted. So we are working on based on these research scholars, and we are focusing some materials view. So if you see the S phase and photoluminescence characteristics, so we have to know about some basic principle of luminescence. Okay, so luminescence is basically a phenomenon of light when occurring when excited electrons emit luminescence. Then you can say thermoluminescence, that is affected by heating, and by free and electroluminescence electric current. And we are focusing. So if you see the diagram here, first of all, you have to see the basically this is called transition. So what is called radiative transition? Purely a absorption is molecules to the surrounding. So there are different states or excited states are there. From excited states, there is some like dissipation of energy will take place. So that depends on the host, and that depends also on the dopant concentration. So if your more dopants are there, so somehow the excited states, they are they are dissipating energy. So there is no chance of returning back to its ground state. So that is related to quenching effect, dopant quenching or concentration quenching. So one is another is called, your second is internal conversion. So you can say internal conversion is a vibrational state of electronic excited state that is coupled to a state of lower excited state. So there is a internal connection between these two states, excited states, and that is if the energy means whatever the non-radiative transition that gives a radiative or emission occurs from the excited state to the different ground states, then it is called fluorescence. That fluorescence generally we observe if it is less than 10 nanosecond, that is called fluorescence. Another type of fluorescence under this photoluminescence, that is called inter-system crossing. So inter-system crossing is related to a spin multiplicity and spin orbital coupling. So if it is a metastable state, then it passes from excited states to this metastable state through this inter-system crossing, and if finally gives straight to a emission from the states to the ground state, then it is called phosphorescence. So this phosphorescence is generally for greater than 10 nanoseconds. So under this fluorescence and phosphorescence, that is under photoluminescence emission. Next is we are generally called phosphor material. So phosphor material is like phosphorescence or phosphor type material, and if you see the phosphor materials, the matrix is there. You can say host also, and activators. Activators, what we do? Okay, so generally these phosphor materials are inorganic. Some organic is there, but inorganic, insulating, and solid materials that efficiently emit light. So these activators, you can say the like rare earth ions or non-rare earth ions. So these rare earth ions, as we are dealing with this rare earth doped materials. So if you see the rare earth doped elements, there are 17 elements are there. Out of 17 elements, 15 lanthanides with atomic number 57, lanthanum to 70 and lutetium, and plus yttrium and scandium. So these are the 17 rare earth based elements. You can say here also you can see the 17 or the some of the examples of your rare earth ions, and these rare earth ions are better luminescence centers. Basically this is the center and this is the host. So we have to dope these rare earth ions to a host material, and this transition of metal elements because of the 4F intracell transitions originate narrow and intense emission lines. Generally, if you see the europium, cerium, and terbium, what is we are dealing with europium and cerium and terbium, that gives a narrow, basically europium and terbium gives a narrow emission lines, but cerium gives a broad emission lines depending on the transition type. Okay, so this why we are dealing with europium and cerium and terbium, because europium generally gives red emission and cerium gives yellow plus blue emission, and terbium say green emission. So for let's say one particular, I'll give one example, like give a white light applications. So white light applications, if you combination of these three, let's say blue plus red plus green, this you can get white light, or you can get a yellow plus blue, this gives white light. So combination of this blue, red, and green type phosphor materials, and with proper concentration or weight percentage or volume percentage, you can get a white light. Generally for blue LED coating with red and green phosphor, and yellow phosphor with blue LED, so that also gives white light. So this rare earth doped we have focused in this lecture. So by varying the composition of activators and some processing parameters, you can get multiple application in luminescence field, and that can be possible. So basic principle of this energy level structure of europium 3+, if you see the electronic configuration of europium 3+, that is 60 electrons are there. So xenon plus 4 plus 4f orbital, the 6. So the electrons arranged in an orbital of 4f block, and arranged electrons are like this is f block, so 14. So electrons should be there, but this is f6, 4f6. So 1, 2, 3, 4, 5, 6. So this transition of electrons are followed by the general relation, this one, 2s1 plus 2s plus 1 Lj, where the L is represent azimuthal quantum number, and it is a summation of this all this minus 1 into, means if you consider the spin of 1 minus 3, this plus all combination of this part. the spin orbital quantum number, S is the spin orbital quantum number, then because it is a half spin, so half up, if you consider, then you can get 3. So 2s plus 1 is 7. So generally this whatever the 7 and F term is there for europium case, europium 3 plus. So this J is the angular quantum number, and it is range from L plus L to L minus S. So if it is L is 3 and S is 3, the possible J values are 6, 5, 4, 3, 2, 1, 0. So this you can say 7, 1, 2, 3, 4, 5, 6, 7. So possible europium ions transition are 7F0 to 7FC. If L equal to 0, then if L equal to 0, S, 1 P, and 2 it is D, 3 is F, and 4 is G. So if it is L3 here, so we are considering F. So that is, and this is the different transitions from 7F0 to 7F6. So because the term with the highest spin multiplicity of 4f configuration is a septet. So the order of energies of different levels of 7f term, like 7f0 is less than 7f1, like that way 7f6 by the Horn's rule. So as of the one of the rules suggests that if the electronic cell that are less than the half filled, the ground state as a possible lowest possible J value. So in case of europium ions, this 5d0 excited state to J levels of the ground term of 7f. So there is a possible energy transition of europium 3 plus based like 5d0 to 7f0, 5d0 to 7f1, 5d0 to 7f2, like that way with 5d0 to 7f6. So most of the transition of this europium 3 plus are considered as electric dipole transition, and one possible term is magnetic dipole transition. If you see the 5d0 to 7f0 and to this range, this is called electric dipole transition, except this 5d0 to 7f1, where the wavelength that is considered for 585 to 600, and for 5d0 to 7f, this is the wavelength 570 to 585. Most important factor is 5d0 to 7f1, f2, that is a strong value or very strong, and that is a hypersensitive transition, and intensity very strongly depend on environment. Environment means how the europium ions are distributed, that also depends on hypersensitive transition. We are dealing with, for europium case, we are dealing with these two because the most intense is very your 610 to 630, because it is in red range, 5d0 to 7f2, and 5d0 to 7f1, that is a magnetic dipole transition, that is around 590, and it is also strong, and intensity largely independent of the environment. This is independent, but this is hypersensitive transition. All other peaks are very weak or small. So that means the whatever. Hello. Okay. Okay, so these are the different transitions of europium ions. With considering these two are the most, or the first most is this one, 5d0 to 7f2 transition around red region, and this one is 5d0 to 7f1, that is for orange region. So that is why we are getting a reddish orange or reddish orange type orange type phosphor materials if you dope the europium ions. So what we see here, the similar thing you can say, this transition, if you pass some different higher some energy, if you pass through this material, then different transition occurs. So similarly, you can get a photoluminescence PL spectra of europium ions. If you see, there are 5d to 7f2. This is for orange emission, and this is for red emission. Okay, so as I told here, this is this is electric dipole transition, and this is magnetic dipole transition, and this is related to your orange emission, and this is red emission. So this generally, if you see europium 3 plus, if you add, then you will get orange plus red. And if you this intensity variation of this orange and red, you can change by decreasing the size. If you reduce the size, then you can dominate the red emission and you can get a deep red phosphor materials. Okay, and that is related to asymmetric ratio, that is R by O ratio. This intensity of 5D 0 to 7F2, that is red contribution, and if it is orange contribution, this is red contribution, this is orange contribution. That is why you can get a red and orange. But somehow if you get a very, let's say this peak will be like here, then this will be bigger, then your R contribution is more. So that is why you can get a deep red, or it is red chromaticity or red color coordinates that close to the ideal red chromaticity. That is possible by decreasing the particle size, creating defects, and lot of things are there we'll discuss. uh, and just it is fine for you all.
Yes, sir. Yes, sir.
Okay, fine. So one is for European case, that is called Arbe ratio. Another is called CI coordinates to determine the color emission of the phosphor materials, and color purity. Color purity is the quality of color emission, how much percentage or purity of your color emission. Another is CCT. CCT is correlated color temperature, that is related to how it is applicable in living and commercial lighting applications. So point is that, can you make a deep red by decreasing this 5 degrees to 7F1 transition, by increasing this transition? So it is possible. So another characteristics of, because we are dealing with europium and terbium and cerium, so we'll give you some examples or characteristic transition of terbium ions in a host material. So if you see the terbium ion transition, similarly you can say the 5D4 is the lowest excited state, and the emission transitions are this one: 5D4 to 7F4 6, 5D4 to 7F5, and like that way. So most important is your green contribution, because it is 550 wavelength. So this contribution is your green contribution, and this contribution is called blue contribution. So this blue and your green contribution gives rise to your green emission in case of a terbium ions. Similarly for slightly different for your cerium ions, because cerium ions has 4F and 5D cell, a 5D orbital. That 5D one is the lowest excited state, and it allows the 5D to 4F transition, because 5D has non-ready transition, and that gives to a different two splitting of 2F 2F 7 by 2 and 2F 5 by 2. So these are the splitting of 4F transition, and it is related to DF 5D 4F transition. But in case of a europium and terbium, that is related to FF transition. And this gives a cerium, because cerium is mostly gives you a blue emission, because it is 480 nanometer and 525 nanometer. This is blue emission, and this is for yellow emission. So cerium gives a blue or yellow emission type. So this gives a like cerium doped yak. So you can see this is contribution of blue emission, and this is contribution of your green emission. Yellow emission. So that means yellow and green combination, that will give you a cerium doped yak gives a yellow type phosphor. So that yellow phosphor of cerium yak related to if you coat in a blue LED, then you can get a white type emissions. So another characteristics of your CI, your photoluminescence characteristics is CI chromaticity coordinates. Basically, the CI chromaticity coordinates is a two-dimensional coordinate system. Okay, so based on the 1931 graph, CI 1931 graph, so you can say your red contribution and green contribution and blue contribution. So this you are plotting in a two-dimensional figure. So human eye can perceive this color, which are best describe the coordinate xy. So you can see here, this is the y coordinate and this is the x coordinate. Okay, so you can see value is written 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, like that way. Similarly here also in y-axis. So, and generally these CI coordinates can be determined by using the visible region of emission spectrum. Example, 400 to 700 nanometer using PL spectra. So for a three-dimensional, if you see the color coordinates, this is expressed by the x and y, where x is equal to capital X divided by capital X plus y, capital Y plus y z. Similarly, small y means x y coordinates is related to y divided by capital X, capital Y plus capital Z, where x and y z indicates the three stimulus values, where since x y z equal to 1, if you two of the chromaticity coordinates are known, then third is negligible. So basically the CI diagram supports the three-dimensional data to be condensed into two-dimensional data. So this figure, this position is 0.33 and 0.33. So this is called white light generation, this portion. If you get here, then deep red, and here then you're getting a very your green, deep green. So like that way, if you're based on your PL spectra, you can find out the chromaticity coordinates. Another photoluminescence characteristic is called color purity. This color purity of any type of luminescent material was determined by the obtained CI coordinate value x and y using the formula. This formula you can use, where the x s suffix s and x y s are the coordinates of the prepared sample, and x y y I are the coordinates of illuminate point, because we are taking a white point as a standard point. So x and y, and y xd and yd are the coordinates of dominant wavelength. So this is for your ideal red chromaticity coordinates. So based on this, you can calculate the color purity. Another is called correlated color temperature, that determines the application point of view, where your material can be used either in living or commercial lighting application. So this is the formula you can use, McCamey Amplicor formula, and this is your where n is equal to this formula you can put for to determine the color CCT value. And based on the CCT value, generally if it is less than 5000 K, then you can use for living application, or living and commercial lighting applications. Fine, this is up to here. We are basic part is over. Now we'll go to synthesis part. It is fine. Okay. Yes or no, just tell me, because I am just speaking, and sometimes I have to break and I have to ask, are you listening or not? That's why
Yes,
just
sir, yes,
say
sir.
yes. Okay,
Listening,
okay,
sir.
thank you, thank you, thank you, thank you, thank you. So this online system is very, sometimes the speaker speaks a lot but no response from the audience side, then it will be bored. Okay, so let's see. Yeah, true. So actually, the synthesis part, what we are following here, this is I told you the borohydride route. Actually, it is a gelation or precipitation route, but we are using sodium borohydride as a precipitant. So you can say most common precipitating agent like NH4OH. NH4OH is a well established precipitating agent to prepare different oxide materials. But we are using a precursor or precipitating agent like NaBH4. So if you use NaBH4 with water, then it gives a your tetrahydroxyborate plus hydrogen gas bubbles. Okay, and in case of a NH4OH, if you see NH4OH, then you can get a hydroxide ion. And this why I am focusing this gas bubbles here, because these gas bubbles create numerous gas liquid interface, and act as a nucleation center and formation of loose nanocrystals, nanoclusters. And then if you prepare a loose nanopowders or nanoparticles, then if you calcine, then you can get a porous structure during calcination process. How it is possible? I will give you some of the part. Like let's say in a synthesis, you are adding this borohydride or NaBH4 with some, let's say, zirconium oxychloride, ZrOCl2.8H2O. So this zirconium chloride will react with this hydroxy tetrahydroxy borate because OH group is there. Okay, but the how it is forming a network structure.
அதுல பெருசா ரியாக்ட் பண்ண மாட்டேங்கிறாரு அவரு. எனக்கு அது ஒரு பெரிய ஷாக்கா இருக்கு.
So
அப்பா
okay.
வந்து கொஞ்சம் அப்படியே ஷாக் ஆயிடுவாங்க. ஏன்னா அவங்கள நம்ம
Background noise is
Who is making noise this kind of?
kindly mute your phone. Sneha Leo. Okay, so this zirconium ion Zr+4, this Zr+4 and OH ion, that will create a network and forming a ZrOH4 nuclei. ZrOH4 nuclei. These nuclei, how? Because very small size, so highly active, and that will try to minimize the free energy. Okay, always a system try to minimize the free energy to make a stable state. So these gas bubbles, it will play a role. How? This nuclei will attach on this bubble surface and it stable the nuclei of the ZrOH4. So let's say two bubbles are present or more bubbles are present and surface attached with this zirconia ions or nuclei. Then during calcination process, this as these voids present, so these voids will act help, and during calcination the particles growth may suppress, or the control of growth or particle size in nanometer you can get during calcination process. And if two gas bubbles will attach each other, and if you during calcination process, if you heat treated the materials, then this will create a void within the particle, so you can get a porous structure in case of a using this borohydride process. So this is more advantageous to get a various loose nanoparticles, and the growth of the particles you can maintain in nano size, and also you can stabilize the tetragonal phase of zirconia up to moderate temperature. Why I am telling you zirconia particles? Because please mute your mic.
Dr. Sneha, why you not mute your mic?
Okay, thank you. So zirconia, we are focusing here because mostly zirconia is a most stable phase is, you can say, or practical application point of view, tetragonal cubic phase of zirconia, and that can be stable because by decreasing the size of the particle. Generally, Garvey theory, if you see, then less than 30 nanometer if you prepare, then you can stable the tetragonal or cubic phase of zirconia, or by incorporating dopant like yttria stabilized zirconia, calcia stabilized zirconia, magnesia stabilized zirconia. So the stabilization part of tetragonal cubic zirconia phases, that can be by using dopants. Also by rare earth dopants like europium or terbium, you can dope and you can stabilize the tetragonal phase of zirconia. So here what we observe, this is the DTA curve of your zirconia materials, and this DTA curve gives this is the typical DTA curve of zirconia by NH4OH. So generally you can get a exothermic peak around 440 degrees Celsius. So below this temperature, that is in amorphous zirconium hydroxide state, and above this is crystalline zirconia powder. The point is that how by somehow you can increase, can you increase this crystallization temperature so that you can stable the amorphous phase up to moderate temperature, and you can get a pure tetragonal phase up to moderate temperature. We are doing it. We have done the some of the zirconia particles using NaBH4 and by your gelation, precipitation, and constant pH. These are the three different way of synthesis. In gelation, we are just adding the NaBH4. I will write SB, and using zirconium salt, and by adding by addition of the sodium boride into the zirconium salt at some pH, let's say pH 4, generally pH 4, you will get a gelled powder. Means the network structure of the particles or nuclei will form. So that we take the sample and we have dried and calcined, and we have dried, and that as prepared sample we did the DTA. Similarly, if you break the gel and finally addition of more sodium borohydride, then you can precipitate the powder, that is precipitate form. And what is constant pH? Just another a different way of methods, that is we are taking sodium borohydride in a concentrated form and we are adding zirconium salt. So generally sodium borohydride at pH around 10 or 11 around, and this is acidic pH. So if you add, then the pH will increase. To maintain a constant pH and reaction occurs at a constant pH, we have additionally added the sodium borohydride at this position, at this another beaker. So that to maintain a constant pH. So you can see from gelation, you can enhance from 450, you can say 450 degrees Celsius to 600, 622, and 717. That means you are getting a pure tetragonal phase up to or amorphous up to 700 degrees Celsius, and above 717 degrees Celsius you will get a tetragonal phase and very fine size. So to establish that part, how this gelation occurs or the precipitation occurs, that we are discussing about FTIR. So what we have did, the gelation, and after precipitation we keep this sample, we kept this sample for some days, so you can get some borate, some piece of borate we just get from this precursor solution, and we did the FTIR, and you can see this range and this range is related to BO3 and BO4 groups. So so we have analyzed and we have find out how the network structure of this zirconium is taking place during this borohydride synthesis. So you can see ZR with attached with OH, and this OH and OH whole 4. Okay, and you can see here boron BOH whole 4, this hydroxide, tetrahydroxide BOH whole 4, and this is BOH whole 4, and this is BOH whole 4. This is BOH whole 4, BOH whole 4 attached with ZR OH whole 4, and another BOH whole 3 is attached with this ZR atom, ZR molecules. So this is a network structure of BOH whole 3 and BOH whole 4 with ZrOH whole 4. So the BOH whole 3 is basically unstable state, but finally when you do precipitate, then BOH whole 3 that converts to BH whole 4. So what is there, this hydrogen is in between this gel network structure. So in gelation, the hydrogen is trapped. So that is why you are getting a less exothermic peak in DTA in case of a gelation, but in precipitate this is more active. Okay, so that is why you are getting a nuclei of ZrOH whole 4 on the surface of the hydrogen gas bubbles. But in constant pH, as constant pH, the concentration of your gas bubbles is more here, and that is why you are getting a highly loose powder, or you can say very fine powder in case of a constant pH, and that is why your amorphous state to crystallization transition from amorphous to tetragonal transition, you are giving a higher energy. So that means your exothermic peak is shifted to higher energy due to the contribution of hydrogen gas bubbles. So this all we have discussed, and finally you can see the TEM micrographs. Then you can see the one particle around 10 nanometer. If you take the larger length, then 20 or 25 nanometer particle size, and in between the porous structure, pores are present. So that pores is around 2 to 5 nanometers. So you can say mesoporous type materials. And we did some practical application. We have used you have used lead removal and chromium. So it is a selective type. So around after 15 or 20 minutes you can get mostly lead can be removed by these porous materials. So this is all about the synthesis of why we are choosing the sodium borohydride as a precipitating agent, and roll of hydrogen gas, roll of your roll of tetrahydroxyborate and your trihydroxyborate. So if you heat the sample, this is the, you can see the pore morphology or pore connectivity, then materials. You can see the we did some temperature mediated pore geometry, how the pore shape, pore morphology are changing, and pore hysteresis from the as prepared or as synthesized powders to different calcine powders. So you can see the changes of the hysteresis. This is called BET isotherm and adsorption and desorption process. BET hysteresis loop. This is adsorption process and this is the desorption process, and we are getting a different morphology. And you can say this is the typical H2 type pores. Means H2 is basically a bottleneck type pores. Okay, and S3 is typically S3 type is slit type pores. So this is the combination of H2 and S3. So you can see the your these are the slit type pores present on the in the particles. And if you see another, like in the S synthesized, the I'll give some key points, like this is the wide range. So that means the bottles are this is this is the non-saturating type behavior. So we are assuming that pores are interconnected. So one is interconnected, and the pore size is around 4 nanometer, 4.6 nanometer. And this is the interesting part that is related to your wide range, means some volume percentage of pores are present in a wide range. So we are assuming the bottleneck pores are like well connected, interconnected type, like this, a dumbbell shape. So you can, if you heat the temperature, if you heat the sample at 400 degrees Celsius, then this decreases, and finally this is decreasing. So that means this dumbbell shape, it is breaking and forming a network in your bottleneck pores. That is why if you see here, it is 0.24 volume concentration of 0.24, and this is increased to 0.4. That means the bottleneck pores break during calcination process, and the increasing the bottleneck pores to 0.4. So finally you can see the combination or the presence of different types of pores. Like in the S-synthesis powder, we are interconnected ink portal major phase, major pores, and dumbbell shaped pores with the minor phase, and the surface area is 182 meters per meter square per gram. If you heat treated, that bottleneck pores uh, connected or interconnected bottleneck pores, closing of very few bottleneck pores, and typically closing of very bottleneck pores. That is why it is increasing the maximum pore volume, increasing to 0.1 to 0.6. And obviously if you heat the temperature, then surface area decreases. And finally we will get a mixer type ink bottle tape, ink bottle and neck and slit type pores in the 800 degrees Celsius, and complete disappearance of your pores at 1000 degrees Celsius. So this is all about the porous structure, and we are doing it now. This is all about your undoped type materials. Okay, now we'll see the doping type materials. We'll start with cerium. doped zirconia, we are doing some like air and argon atmosphere. Okay, so we have prepared different concentration like 0.1, 0.5, 1 and 3. So different concentration and different atmosphere, air and argon. So what we observe is the strain, what is the defect structure, what is the strain effect on the photoluminescence characteristics. So if you see with increase in concentration, then pure tetragonal phase we are observing up to 3 mole percent in case of a air heat treatment, but in argon the 2 means 0.1 to 0.5 you are getting a amorphous type material, but above 1 mole percent we are getting a tetragonal type material. This is for 600, but if you go for a 800, then air which is tetragonal in case of a 600 Celsius, it is a combination of monoclinic and tetragonal phase. But in argon, it is purely tetragonal. All composition are tetragonal. So how we are giving the powder morphology? So if you see the powder morphology and the histogram of different particles considering 100 number of particles, so the particle size is around 30 nanometers. So that is why we are getting a pure tetragonal with some monoclinic phase. So depending on the concentration. So we did some XPS because if you are hitting in a argon atmosphere, there is a chance that there is a different valence state of cerium. So, but in our case, both means in air and argon, we are getting similar cerium 3 plus. So both sample in argon or at air atmosphere, we are getting 3 plus state of cerium, and this is the excitation spectra, because if you are selecting the which wavelength we are applying, so that you can get a maximum absorption and we can get a emission spectra. So we did the excitation spectra, and around 231 nanometer you are getting a maximum. So we did the emission spectra, and finally what we conclude, the intensity with concentration of cerium, it is increasing in trend. Okay, but in case of a argon atmosphere, nearly constant. So the emission intensity increases with increasing cerium concentration in under air, and that may be in distortion and strain. So we have calculated the strain and particle size, and that we are not focusing, but that is related to your distortion and strain. Similarly, for in case of a argon atmospheric condition, the suppress of your crystalline phase is found to be suppressed up to a certain concentration, and above 1 more percent cerium concentration, pure tetragonal phase is developed. So finally, we have put the we have analyzed the CI coordinates, and it fall in the bluish region. Also, we have determined the powder color under standard UV under standard UV wavelength, that is 254 and 365 nanometer is the standard UV radiation. You can from market you can take the UV light source, and using 254 nanometer and 365 nanometer, we have seen that powder color is bluish in nature, and that is well correlated with the CIE coordinates. Then we can use some practical application point of view. If you see the we have used because it is a single color, so best application is latent fingerprint visualization by blue emissive cerium dot zirconia. So we have used this powder in glass slide and in Indian node. So you can see naked eye, you can see the fingerprints impression on the glass slide, but here we are not able to see in the node, as when it is passed through a wavelength of UV illumination of 254 nanometer, then you can get a bluish emission of your fingerprints, and this you can in the node also. Okay, so that is why you are getting a very good impression on the glass slide and your Indian node. So after 30 days, because you have to see the what is the you have to see how the your fingerprints after some days, how it will evaporate or it is stick to the sample, or you can analyze that part. So you can get the glass slide shows a better impression, but in note we are getting a very hazy type impression, but you can analyze the glass slide sample after 30 days. So there are different levels of visualization of different levels of latent fingerprint. So level 1 is general overview of all types of fingerprints. Then level 2 is basically you have to identify the loop. You can see here, you can say loop here. Okay. And your termination, you can get the like here bifurcation or termination you can see. And your crossover, you can see one, and this is crossover like this. And your bifurcation. So bifurcation is basically your two bifurcation is like this, and then level 3 is sweat pores. So all type of level 1, level 2 and level 3 we are visualized different levels on the fingerprint on the glass slide. So how to characterize that I will discuss in on other materials visualization part. Next is europium doped zirconia under calcine under air atmosphere. So we have seen different composition. If you see here, different composition of europium and in under air atmosphere at 600 degrees Celsius, and this is 600 degrees Celsius, and this is 800 degrees Celsius. And 600 Celsius, only small minor peak of monoclinic phase we are getting, but above 0.5 we are getting a pure tetragonal. And similarly for 1 more percent europium doped we are getting a pure tetragonal. But you can see the 24 nanometer, this is for 600 degrees Celsius and this is for 800. So we are getting a 0.5 more percent europium doped sample at 600 800 degrees Celsius. C is the 1 mole percent of sample 680 Celsius. So we are getting a very fine particles of this part of europium doped zirconia. Now if you see the excitation spectra and emission spectra, considering this three different, one is charge transfer band, and another is called 254 nanometer, 365 nanometer, and 393 and 463. These are the four different wavelength we have chosen based on this excitation spectra. And what we see, the black one, the black spectra, you can see black spectra is slightly different compared to red and blue in all cases, because this it gives a monoclinic phase. The black one is related to monoclinic plus tetragonal. So if involvement of this phase of monoclinic phase, that will give a different spectra compared to your pure tetragonal case. So red and blue are the pure tetragonal case. You can see here the black one is the monoclinic, consist of monoclinic. So here also you can see, but red and blue position of your the 5D02 7F1 transition and 5D02 7F2 transition, these transition are same, but there is a slight difference in the monoclinic case. So we are getting a asymmetry ratio, that is, you know, the asymmetry ratio is contribution of red by R, R by O ratio. The R by ratio at different excitation wavelength, you can see. So all are around except this 365 nanometer, all are around 2 or 3, around close to 3. So based on that, we find out the CI coordinates, and this CI coordinates is false in this region, also in the white region. So typical 254 nanometer and 365 nanometer, if you do, then the samples, it is coming out like pink or reddish type, and this is bluish or nearly white type. So this difference or dual color, one sample with two different excitation wavelength, we are getting two different colors. So based on that, we did some applications that I'll show next slide. So, but in case of an argon atmosphere, so what we observe is a clean phase where these two are amorphous and these are the pure tetragonal case. In case of a 600, wherein 800 we are getting a pure tetragonal case. But if you see the CI diagram, then you can see a different excitation wavelength, we are tuning the color. from USA, you can say the nearly pinkish to slightly pink reddish, and finally here some orange reddish type. So you are tuning the color by changing the different excitation wavelength. So we did some anti-counterfeiting application because two different colors and particular wavelength. So we get some ink, and then finally we have used the logo, means NIT logo, on a screen printing technique. So this ink, luminescent ink, we pass through this screen printing, and we develop the NIT logo, and based on that we are passing at 254 nanometer and 365 nanometer. You can see the two different color, so that you can apply for different applications. Okay, so this is all about your europium doped case. And similarly for terbium doped, so you can see the different phases for terbium doped in AR and argon. This is for 600 AR and argon 600. Similarly for AR 800 and argon 800. So you'll get a combination of, somewhere it can get amorphous material, amorphous type, and somewhere you can get tetragonal. Okay, so it is a very good green dominant, because your green contribution is more, so you can get a green dominant materials. So if you see the CI coordinates, then you can see the materials fall in this region, and for a 6 mole % fall in this region. So typically green type materials of TB doped zirconia. So this is how this slide represents how a rare earth ions distributed in porous zirconia materials. So what we did, the line profile of a but using TEM, and we did the porous structure, because if you consider this the porous particle and the line profile considering here, then this is this part is represent here. Okay, so this is your particle end. Okay, I'll give you I'll give you some more example. This is the particle end. So here there is no this green sorry, blue line is your europium and black line is zirconium. So up to this portion, or here you can see the europium will do some data is request me annotate the shared content. So this this blue is europium ions distribution. Okay, and this is the zirconium ion distribution. So when we go from surface to interior of the particle, the europium ion is absent, whereas zirconium is present. Similarly for here, you can go like this, then zirconium is decreasing and there is no presence of europium. But in this place, in between here, this to this, this is increasing, or you can say somewhere europium and zirconium both are present at this position. But interesting, you can see, can you see a porous structure at this position? The contrast is there, some contrast, you can say different contrast from this place to this place. So you can see if I marked here, then decreases. So that means this porous, this area, the zirconium is decreasing and europium is also decreasing. So you can find out the presence of europium, how it is distributed. Okay, similarly for your terbium doped and co-doped, we also find out the distributions, and also in head-up image with elemental mapping, so we can find out the distribution of europium ions. And
coming from there only.
finally Finally, if you see the application point of view, then combination of europium, cerium, europium,
Message no in group. Just call them.
some background noise is
Why they are leaving just like that?
uh,
I'll inform the HOD. You tell. These many students, we know
Hello,
that
why you are speaking?
you will be got.
Hello,
Tell them.
Linus. Why you
So,
making
Who is there
noise?
in the department? I am coming from there.
okay. So, okay. So, these are the three different materials, cerium, europium, and terbium in air,
You
and
will
you
be
can see
called
the
by
color.
principal or in HOD. That's it.
Similarly, for argon,
Two people are taking
is
attendance.
argon atmosphere, these are the different color you can see. How to make a combination of this? By changing the weight percentage of cerium, europium, terbium, you can see some changes you can finalize, and finally you can see this composition. You can see 1 cerium, 0.5 europium, and 2 terbium. This will give a slightly near whitish, whereas in argon based sample it is a yellow. This is like you can say white, near white, and completely not near. You can change, you can, by this combination, by changing the concentration of different concentration, you can get either white or bluish, yellowish white type materials. So another example I will give you, europium doped zinc oxide. So we are talking about phase and some impurity phase in this case. So if you heat the materials from 200 to 1200, so pure phase you are getting up to here, pure phase, but above 1000 to 1200 you are getting an impurity phase. So we are talking about, in this work we are talking about how this impurity phase or secondary phase influence the photoluminescence characteristics. So we are find out, so what is the phase composition of this. So in that case, pure europium borate without any zinc based precursor, so we are getting a UbO3, and these two phases we are getting. Okay, some borate phase you can take. So this sample consists of some borate and zinc oxide pure phase. So if you do the FTR spectra, then also you can find out the borate phase. This group is decreasing. You can see this decreasing. Okay, so finally you can get a negligible bio
Where did
group,
they go?
and your zinc oxide,
Not in
presence
the
of zinc oxide
department.
is also here, metal oxygen bond. So from FTR you can find out the presence of FTR and XRD spectra. You can find out the presence of borate phase. So how this influence the morphology? We are taking three different precursors. One is nitrate, another is acetate and chloride. So what we observe in acetate precursor, we are getting a rod, or you can say flower like particles which consist of rods, whereas in nitrate and chloride we are getting a very spherical, or you can say elliptical type particles. So the all depends on the synthesis part. Okay, so basically if you see the nitrate and chloride, these two are acidic in nature, whereas in acetate that is slightly acidic in nature. So depending on the acidic nature, the reaction of your precursors, if you can change those acetate, chloride and nitrate, then these two are forming HCl and your HNO3. Okay, more acidic in nature, but this one is less acidic in nature. So that is why your reaction, your formation of nuclei, okay, formation of nuclei at a certain period of time, you can get more number of nuclei in case of a chloride and nitrate case. So that is why their particles are agglomerated in nature. But in acetate, as the in a certain in a wide temperature, in a nucleation sites are more, or concentration of nucleation sites are more, so they are they are aggregates of particles and forming a rod type, and to minimize the total overall surface energy, this rod shape will attach to a flower like structure. Okay, so this is the basic principle of the formation of different morphology. And if you see the different PL spectra, so you can see the 5FD02 7F, this red contribution is more, and we are getting, this is the red chromatic coordinate, ideal red chromatic coordinate, the white dot, and whatever we are prepared sample, this is all lies in this region. Okay, whatever acetate or nitrate or chloride based precursor with different calcination temperature, all lies in this range. Okay, another part, the contribution of, I'll show you the skip words like the this presence of this zinc oxide with europium borate. So it is not hampering the R by ratio, it is increasing at 1200 degrees Celsius. The borate, whatever presence of borate, that also increases the R by ratio. That means the photoluminescence chromaticity, it is not hampered by the secondary phase. It is rather moderately improve the secondary phase, improve the photoluminescence characteristic. Also you can see here. So based on that, if you go for higher mole percent, then you can see the evolution of your secondary phase at 800 degrees Celsius, because this is all about 3 mole percent. But if you go for a higher concentration of europium, then you can get a evolution of tetragonal evolution of europium borate and some amorphous nature of your borate phase in case of a acetate and chloride phase, and this is for nitrate case. So also you can see here, also you can see R by ratio in presence of a your borate phase, it is also increasing. And you can see here, this is the black part, this is the indication of your presence of your borate phase. Okay, so we have analyzed, and finally you can see the CI coordinate fall in this range. And color purity, what is we observe, is more than 80%, more than, depending on the concentration, except this 1200 degrees Celsius. But mostly it is if you consider the reference of 80% color purity, and we are getting a value of more than 80% with at particular concentration at 3 mole percent, you can say. Okay, so for practical application point of view, we have taken the acetate based precursor with 400 degrees Celsius sample for latent fingerprint, and for anti-counterfeiting the 600 degrees Celsius sample, because based on the color purity, it is more than 80% and asymmetry ratio. Also it is lies in the close to this square, this ideal red chromaticity. Okay, this one, ideal red chromaticity. So all after analyzing the phase and photoluminescence characteristics, we did the latent fingerprint using this europium doped zinc oxide. What we did, by cleaning the thumb on the surface, cleaning the thumb, then we press the thumb on the glass substrate, and then we pour the powder, nano powder, and then finally passing the UV lamp, and then we capture the latent fingerprint image under UV light source. So based on that, we have used polymer based, like your polymer credit card, and then metal, stapler, glass slide, and curved. Curved means is a tape, brown tape. So you can see the acetate based sample gives a better result compared to nitrate and chloride. Okay, so depending on the materials, size, morphology, all things, you can optimize the visualization and identification of latent fingerprint. So we have analyzed manually by this visualization of latent fingerprint developed on a glass slide. So all type of like level 1 and level 2, level 1 and level 2 like bifurcation, island, eye, regending, crossover, and sweat pores level 3. So all type of information you are getting, and this is the pixel profile Pixel profile indicates the area, indicates the vertical rectangular shape on a visualized latent fingerprint to determine the sensitivity. The fluctuation of red pixel value with ridge and furrows over the few papillary bridges highlighted in horizontal range. So that means how you can see the material distribution at this range in this region, because it is low, means your material is sufficiently focused on the ridge portion. Okay, these are the ridge area, means whatever line material is deposited on this line. Okay, the fingerprint line. So to analyze the qualitative analysis performed to indicate how close the latent fingerprint to the scanned fingerprint. So obviously we have to match with the scanned fingerprint. So how much the analysis include examining the fingerprint minutia to find out potential matches and establishing the agreement and disagreement between unknown and known fingerprint. So in a crime scene, whenever you are getting a fingerprint from the crime scene and you have to match with the established known fingerprint, then only you can say find out the possibility or how much matching is observed, matching is occurred, that you can find out the known sample. Okay, so based on the viewpoint, the following experiments are performed to check the quality of the latent fingerprint, both scanned and latent fingerprint. And these are basically with the help of computer science department image processing. Dr. Pankaj Kumar Shah, we have analyzed we have analyzed the extracted the minutia, whatever the critical minutia we have exercised, and we have meshed through a set of standard algorithm. So whatever steps we have used, that is like image enhancement, minutia extraction, minutia matching, and these are the steps we have involved. And the programming, whatever standard algorithm we are following, and by different steps like normalization, orientation estimation, ridge frequency estimation, region mask generation, filtering, thinning, and minutia extraction and minutia matching. So I'll just overlook this part because this is the scanned fingerprint, okay, by using some machine. Okay, and this is the fingerprint on the glass slide. So this is called latent fingerprint and this is called scan fingerprint. And uh, by 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 taking two persons thumb finger, so we have analyzed on different surfaces. Okay, by programming we have enhanced the fingerprint images, then we thin the fingerprint, then minutia present at dots. So you can see the dots where the red dots is the ridge ending. You can see this is the ridge ending, this is the ridge ending, this is the ridge ending, and blue dots is the ridge bifurcation. So you can see this is the bifurcation, the blue dots is the bifurcations. So based on this part, so we have two persons, one is left thumb finger of A, right thumb finger of A, left thumb finger of B, right thumb finger of B. So we have analyzed and find out the appropriate part, and we can see the typical like right thumb person. We know the person. Okay, we know the analysis. We know the which one is the person's thumb. Okay, so by cross checking, so we get a better average score for a right thumb person A on the brown tape, credit card, stapler, and glass. So you can see for other persons, this person's is getting higher value. So we are concluding that we are approximately matching with the by this analysis, and you can see by overlapping the minutia image scan fingerprint, this is the scan fingerprint, and this is the minutia image of latent fingerprint. So if you overlap these two like this, then we can almost match the your minutia direction based on the minutia direction, and your minutia based matching image. So based on that, you can see the how perfection or how quality of your matching process is established. We are established. So another is anti-counterfeiting applications that we have used this powder 400 degrees Celsius europium doped zinc oxide powder on a QR code, and we scan the in the screen printing technique, and under visible light when we pass and if you can scan, then you are not getting the QR code and not readable. But if you pass under UV lamp and the QR code is readable. Okay, so based on that, we can use in anti-counterfeiting applications. I'll take another 5 minutes. So another type is YBO3 based phosphor materials. This is called europium doped, this is terbium doped, and this is europium and terbium. Okay, europium and terbium mixed doped. So based on that, you can see the by different excitation wavelength we can uh, vary the color coordinates, or in case of europium, also in case of a terbium. But in combination of three europium and 5 terbium, we are getting a maximum in the white light region. So single phase white light region, and we compare with the literature. This A and B are the two different literature, where C is our sample and it is also matches with the literature value, and we are getting a white light phosphor materials. So based on that, we coat on the blue LED. This is the naked blue LED where blue light is there. When coat on the blue LED, we are getting a white emission. And for security and anti-fraud domains, we have used different types of pattern, and this is also polymer based for photoluminescence film. And you can see here nothing is in naked eye, you cannot see anything, but you can see NIT is written, and this is the logo by screen printing. Then security anti-counterfeiting anti-fraud domains, we have made inks, and we can write some NIT and fingerprint analysis. Also we can different types of color tuning and printing coding designs that can be scrutinized for anti-forgery. So these are the different colors or multi-colors you can prepare. These two are related to your non-rare earth based strontium aluminate based phosphor, strontium aluminate. But other things are related to YBO3 materials. Okay, so this is different concentration. This is terbium doped, and these are the europium doped, and these are the different excitation wavelength. So one wavelength you are getting a blue, another wavelength you are getting a green, but different compositions are there. So you can get a near white light made powdery also, you can get like here also. So this is the combination of U and TB doped your YBO3. So this is all about my work. I will not summarize, but summary is like that. The borohydride synthesis is really a very good precipitating agent to prepare different types of oxide materials, and because due to contribution of hydrogen gas bubbles, and for cerium, terbium, and europium, and combination of all you can prepare, and you can prepare for different applications like your multicolor tuning, white light generation, anti-counterfeiting, and for anti-forgery applications. So these are the different applications point of view, and I will like to thank NIT Rourkela, IIT Kharagpur, IIT Bhubaneswar, SN Bose, National Center for Basic Science, BIT Vellore, Cliff Kerala, and Professor Pankaj Kumar Shah, Computer Science Department, NIT Rourkela, and my PhD scholar, especially all these works are related to my PhD scholars. So Subrat, Nadia, Arun, Sri Subham, and Rahul Singh, and Abhishek King, Srinivas Lupachari, Rahul Anand, and Murdula Ghosh. And also I'd like to thank MTech students Ankit, Akil Ansari, and my funding agencies, CISR, Government of India, Nano Mission, DST, and BRNS. These are the agencies we have given. They have given the sponsorship projects and funding the students as well. I also like to thank Professor Bibu Prasad Swami for coordinating this WhatsApp and given an opportunity to me to talk about my work, and I hope all we have learned something from this WhatsApp and also from this lecture. Thank you very much.
Thank you very much, Professor Vibhuti Bhushan Nayak. If any questions from audience, please ask. Any questions from audience? I think there is no questions. So I should...
all have no, all have understood, or
anyway.
Okay. Thank you.
So I have only one question.
Yes, sure.
How can you control the cross-sectioning? So from fluorescence to phosphorescence. So whether there is any process to control. Okay. This.
Okay. So point is that first of all, you have to see the host type material, what type of host materials you are choosing. Second is concentration. Okay, sometimes if your more concentration is there, then there is a chance that you will get your non-radiative transitions that will disappear. Okay, and that type of material you can get a fluorescence only. But sometimes if you optimize the concentration and temperature part, then you can get a phosphorescence type.
How the doping concentration depends the fluorescent and phosphorescence behavior.
Dopant, like
because
what?
I didn't see this this in any your PPT the presentation that the dopant concentration with the luminescent behavior.
The dopant concentration, we have slides, but as I have to discuss the application part and some of the important part that we have skipped. Okay, but point is that if you add more dopant, then sometimes you can get a quenching effect will occurs. So quenching is one part, like concentration quenching. So that we observe in our material.
Okay. So any more questions from your from audience? I think I thank to Professor Vibhuti Bhushan Nayak for his wonderful and sharing his work. Though actually the many audience from different department, I don't know if they gain something, and maybe their research will develop in new dimension. So anyway, thank you very much. And we close this session for today. Tomorrow exactly 10 o'clock we'll again meet, and there is many 3 lectures from tomorrow that is from 3 different institutes. So I will request everybody should join these things. Morning session, there is Dr. Manoranjan Kara from IIT Patna. Then Dr. Jochendra Giri from IIT Hyderabad, and Satyajit Sahu from IIT Jodhpur. So 3 very important talk is there. And for this, I close this session and thank to Professor Nayak for his. Of course, we will again meet any other talk. Okay, thank you very much.
Thank you.
And a good day for everyone.
Thank you all.
So I close this meeting now. Okay.
Okay, sir. It was a nice session. Thank you.
Sir. चलो आज ही
லொகேஷன்ல ஸ்டார்ட் இந்த வினிதா மேம் 24 23 இருக்காங்க அதான் வாட்ஸ்அப் நம்பர் 9841 8841 182 இந்த மாதிரி தெரியும் ஓகே நிறைய பேர் தேங்க்ஸ் எல்லாருமே இல்ல இது எல்லாரும் கேட்டாங்க நிறைய ஸ்டாஃப் கேட்டாங்க அதான் நான் நீ ப்ரெஷர் நீ பட் அவங்க எப்படி சொல்றாங்க இன்னொரு ஸ்டாஃப் வந்து எக்ஸ்பீரியன்ஸ் அதாவது அவங்க அந்த எக்ஸ்பீரியன்ஸ் From the position of